Now we are going to discuss about the D flip-flop. You can see clearly this is a D, this is a Q and this is a Q bar. So this is a clock signal. So now I am going to give a random D input like this. So this is a D input I am going to give like this. So now I am going to explain, suppose the clock signal, a clock signal is given. So I will explain about we can say that basically the high level triggering, or we can say the low level triggering and the edge positive triggering and then maybe edge triggering. So now we will discuss each and every aspect of this one. So this is the general clock we are going to give in this fashion. So this is the clock signal. See, whenever the clock signal is, whenever this is going to act only for the high level triggering. So whenever high level triggering means whenever the clock is equal to 1, then whatever the input is going to pass through the output. Suppose if the clock is equal to 0 means it is going to stay in the memory state. So whatever the previous output, it is going to stay for the time. So now you can see clearly for a high level. So you can see, let me assume initially the output is equal to 0 because the clock is 0 here. Initially I am going to assume the output is equal to 0. Say at this time, again the clock is active. So clock is active means whatever the input, same thing we are going to get output also. So here input is 1. Here input is 1. So we are going to get same thing. Again here input is 0. Same it is going to follow whatever the input, same thing it is going to follow in this region. Whenever the clock is 1, same thing it is going to follow. So but after this, the clock is 0. So clock is 0 means whatever the previous state, same thing now is going to present. But the previous state is 1, so therefore it is going to have the same state up to again the clock is equal to 1. So again after here, again we can say clock is equal to high. So clock is equal to high means whatever the input, same thing it is going to follow. So it is going to follow exactly whatever the input is there. So it is going to follow like this for all the time until the clock is high. So this is the output that we are going to get. Whenever the clock is equal to high level triggering means whenever the clock is equal to high level, whatever the input, same thing we are going to see in the output. Whenever the clock is equal to 0, means it is going to stay in memory state, means whatever the previous output, same thing it is going to present. So now we'll see if it is a low level triggering. See, whenever the clock is low level triggering means whenever the clock is equal to low, then whatever the input, same thing it is going to become output. And whenever the clock is equal to high, it is in the off state, so therefore it is going to act like a memory. So you can see clearly here the clock is 0. So clock is 0 means whatever the input, same thing it is going to follow up to here. Up to here it is going to follow same thing. Again same thing it is going to follow. But after here you can see clock is high. So clock is high means we can say simply it is said to be off. Off means it is having a memory state. So previous state is 1. So it is remain for up to here. Again it is going to present here. But after that clock is 0. So clock is 0 means it is active. So whatever the input, same thing it is going to present. So you can say up to here it is same. Again clock is high. So clock is high means it is in the memory state. So memory state means what is the previous state, same thing it is going to present. So this is the clock output that we are going to get for low level triggering. Suppose for positive edge triggering. For positive edge triggering means I already told you, positive edge triggering means at rise, whenever the clock is rising from 0 to 1, it is said to be positive edge triggering. So at this instant only, whatever the input is going to pass to the output. In the remaining stages, it is going to act like a memory state. So whatever the previous state, it is going to present in the output also. So you can see clearly now. So initially I am going to assume the clock output is the Q is equal to 0. But here, if you see clearly, there is the rising edge of clock. So rising edge of clock. So therefore, whenever there is a rising edge of clock, so it is going to see what is the input. So at this it is going to see what is the input. The input is equal to 1. So therefore we are going to get this value. So it is going to get this all value again for up to clock rise. So again there is a clock rise here. So clock rise means again it is going to see what is the output. It is the input it is 1. So therefore again it is going to present like this. Again it is going to present like this. So whenever at positive edge triggering only the clock is going to see what is the input, same thing we are going to get in the output. But the remaining time it is going to always stay in the memory state. So whatever the previous output, it is going to present for the same time. So this is basically positive edge triggering. So now go for the negative edge triggering. Negative edge triggering means whenever the clock is moving from 1 to 0, it is called as negative edge triggering. At that instant it is going to see the input and same the output will be same as the input. So this is basically negative edge triggering. In the remaining time it is going to act in a memory state. So initially I am going to assume the state is 0. So here again up to here it is same. But after here we can see there is a negative edge triggering. So clock is signal is going from high to low. So negative edge triggering means it is going to become active and it is going to see what is the input. Input is 1. So it is going to have the input is 1 for all this time because there is nothing again. There is no negative edge triggering again. So it is going to have this shape. So you can see basically, so this is the clock. So we can have a high level triggering, low level triggering, positive triggering and negative triggering. So for different triggerings of the clocks, so these are the different outputs that we are going to get for this common input. So for this common input, for different types of triggering, high level triggering, low level triggering, positive triggering, negative triggering, so we are going to get these different types of outputs we are going to get across the queue. So this is the basic meaning of this diagram. So this is the point that you always have to keep in your mind. So now we will discuss about the race around condition. So race around condition we are going to see clearly here. See I already told you this is JK flip flop. JK flip flop is for SR flip flop. We are going to give feedbacks like this. So if we give a feedback like this from Q bar to J and Q to K, if you give input like this, so I already told you this is going to become JK flip flop. If you are not going to give this feedback means it is basically it is going to become basically a simply SR flip flop. But if you give feedback in this manner, it is going to become JK flip flop. I already told you. So now I am going to see the condition, only the race around condition. I already told you what is the meaning of race around or turbulent condition. It is a continuous change of 0 to 1 in a very speed manner. Whenever J is equal to K is equal to 1, the output is going to change very faster because of this feedback. So now we will discuss something more about this one. So this is JK flip flop. I am going to assume J is equal to K is equal to 1. So again, so this is the clock pulse we are going to do. So whenever the clock is 1, so whenever the clock is 1, the clock is 0 means it is in the memory state. It is in the memory state. So what are the previous output? Same thing we are going to get now. But whenever the clock is equal to 1 and J is equal to K is equal to 1, I already told you the system is in the turbulent condition. Turbulent means race around condition means you can see clearly the Q is changing very fast from high to low, low to high, high to low, low to high, high to low, low to high, high to low, low to high. You can see clearly it is changing very fast. The amount of variation is like a Shikshikabdi Express. It is changing very speed, very speed. The output is changing very faster because of this feedback. So you can see it is changing from 1 to 0, 0 to 1 like a super fast express. So this is basically ideal output. It is called as the ideal output when there is no delay. Suppose what happens? Suppose when there is some delay, DMS just shift the signal by small amount of angle. So if you shift the signal by small amount of angle, then we are going to get this is called as the suppose when delay is equal to 1 nanosecond, just shift the signal by some amount of forward. So this is called as the when delay is there. So this is the signal that we are going to get when some delay is there. So we can say simply this is the meaning of this one. So this is the ideal output. If suppose some delay is there, we have to shift the signal to the right side by small amount of TPD. So TPD is called the propagation delay. So you can see clearly the propagation delay TPD is always lesser than the pulse width. So you can see this is the pulse width. So TPD is always lesser than the pulse width. It is lesser than the clock pulse. So time clock pulse. So this is lesser. See, this TPD is lesser than this clock pulse. This clock pulse is less than total time period of the clock. So we can say the propagation delay is lesser than the pulse width of this clock pulse. It is lesser than the overall time clock period. So this is the point that you always have to keep in the mind. So we can say here whenever you keep J is equal to K is equal to 1 and clock is equal to 1, the output is going to change very faster like a super fast express. So like this it is going to change continuously. This is called as a turbulent condition or race around condition. So this is ideal output. If there is some delay, we have to shift the signal with small amount of delay. This is called the propagation delay. So propagation delay is always lesser than the T pulse width and D dash with is lesser than the T clock. So this is the point that you always have to keep in your mind. Suppose now what I am going to do now basically is here. Say I want to control the speed. Suppose if you want to control the speed, then I have to go for the master slave flip-flop. Means I have to make this one. I have one more thing. So this is one thing. I have to make copy paste and I have to keep under here and then I have to get the feedback. So this is called as a master slave. So if you do like that, it is going to control the speed of variation. It is going to control that. Means this will never change like a super fast express. It will vary very slowly. The amount of variation is in our control. It can be very slowly varying. If you take another copy of this one and if you keep that in front of this and then if you give feedback, then it is going to become a JK flip, master slave flip-flop, and then we are going to control this variation and then we are going to control this amount of variation of the speed. So now we will discuss about this one. So this is called as a master slave JK flip-flop. I already told you this is I already told you this is the thing that we have already seen. So now you have to copy this one and paste another thing here, same identical, copy paste. This thing again you have to keep here another thing. So you can see clearly this you have to give as a clock here. So this you have to give clock here with a NOT gate. If it is the high means it will become low. Suppose if it is the high means this is in the active region and this is in the memory state. Again if this is low means this is the memory state and this is in the running condition. So like that. So from here you have to take the feedback and you have to give it here, and from here you take the feedback and give it to here. So this is the same identical. You have to keep this same identical here and then you have to keep the NOT gate between this one. So if one is in the active means other is in the memory state. If one is in the memory state means other is in the active. So we can say one is the master and the other is slave. So whatever this output is going to follow by the same output. So whatever this output, it is going to follow through this one. So therefore, the output is going to first come here and then it is going to travel to here. So we can say this is called the master and this is called as the slave. So whatever the master output is going to come to the slave. So we can say this is called as the master slave JK flip-flop. So now I am going to assume J is equal to K is equal to 1. J is equal to K is equal to 1 and I am going to give the clock like this. So clock like this. You can see this first cycle, this master is going to become active when the clock is equal to 1 and the slave is going to become active when the clock is equal to 0 because there is a NOT gate here. So this is a part that you always have to keep in mind. So this is QM, this is QM bar, this is QS and this is QS bar. Means these are the outputs of master flip-flop and these are the outputs of the slave flip-flop. So now you can see clearly we are going to give clock in this manner. I am going to give clock in this manner. So therefore it is going to be same as negative triggering output. So whatever the output QS, it is going to activate a negative edge triggering flip-flop. So you can see clearly there is a negative edge triggering here. Up to here the output is 0. Then the output is going to change whenever there is a negative edge triggering. So therefore it is going to go like this. So we can say that the output is going to vary whenever there is a negative edge triggering like this. Means the circuit is going to function like a whenever there is a negative triggering, the output QS is going to get changed. So now you can see the variation of the output is very slow. Whereas in the previous case, very speed of variation. But now you can see clearly the variation of the output is very slow because we are controlling the amount of variation. So we are controlling the speed of variation with the help of this master slave JK flip-flop. So this is the point that you always have to keep in your mind. So whatever this QS, it is a output variation is like it is going to activate the same as a negative triggering output. Whenever there is a negative triggering, the output is going to be changed from 0 to 1 and 1 to 0. So it is acting same as negative triggering output. So this is the point that you always have to keep in your mind. So this is the master flip-flop and this is the slave flip-flop. And these are the points that you always have to keep in your mind. So now we will discuss about the master slave D flip-flop. So now we will discuss about the master slave D flip-flop. Whereas this is called the master slave JK flip flop, but this is the master slave B flip flop. You can see clearly this is the master and this is the slave. So master B flip flop, slave, I can see slave B flip flop. So it's a B, QM, QM bar, D, QS, QS bar. This is a clock signal and we have to keep an OR gate here. So it is going to perform like this. So this is the input gate. So therefore, now you can see clearly, this is the clock I am going to give. This is the clock I am going to give, and I am going to give random input like this. So this is the random input like this. So now I will tell you regarding the master output and the slave output. So listen carefully. See master output. See whenever the clock is high. So whenever the clock is high, listen carefully. Whenever the clock is high, this master is going to get activated. Then whatever the input, same thing we are going to get. We are going to get across the QM. So you can see clearly. So now initially the clock is 0 up to here. So I am going to assume initial output is 0. So it is 0. So whenever the clock is high, then whatever the input, same thing we are going to get. So up to here, whatever the input, same thing we are going to get. Same figure, this exact figure we are going to get here. So same thing I have drawn. Same input figure I have drawn. But again the clock is 0. So from here the clock is 0. From here clock is 0 means we can say memory state. So memory state means whatever the previous output, same thing is going to stay. So previous output is 1, so it is going to stay until the again we are going to get clock high. So again there is a clock high. So clock high means whatever the input, same thing we are going to get. So input is 0, so it is also 0. So this is the basically QM. QM we are each output of the master flip flop we are going to get. So now we are going to do about the QS. So how QS is going to get. And already told you, see, this slave flip flop is going to active whenever the clock is equal to 0. So whenever the clock is equal to 0, whatever the input across this B, same thing we are going to get across the QS. If clock is equal to I, this is in the off state, so it is in the memory state. So now, listen carefully. If clock is equal to no, so slave flip flop is active. So whatever the QM, same thing we are going to get. So whatever the QM is 0, so same thing we are going to get. But here clock is equal to I means it is inactive. So whatever the previous state, it is going to same stay here also. So again this 0 up to here. Again here clock is 0. So clock is 0 means again slave flip flop is active. So whatever the QM, same thing that we are going to get. So QM is 1, same thing we are going to get up to here. Again if you see clearly, again what happened? Again here the clock is equal to active. So clock is equal to active means, say clock is equal to I means it is inactive, slave flip flop is inactive. So therefore whatever the previous output, same thing that we are going to get. Same thing that we are going to get. So this is what I am trying to tell you. So if you see clearly whatever the QS output is similar like NATH triggering. So whenever the NATH triggering, the output is changing. See clearly. So this is a NATH triggering. So whenever there is a NATH triggering, the output is changing. Again if there is a NATH triggering, again the output will change. So we can say the QS output is similarly to the NATH triggering of the clock. Whenever there is a NATH triggering of the clock, the output is changing. So this is the concept that we always have to keep in the mind. So for master flip flop, whenever the clock is high, then whatever this input, same thing we are going to get across the QM. Suppose if clock is equal to 0 means it is going to be in a memory state. So whatever the previous input, whatever the previous output, it is going to present in the same state. Similarly for the slave flip flop, whenever the clock is 0, it is in the active mode. So whatever the input be, it will be same across the QS. Suppose if the clock is equal to high, means this is in the memory state. So therefore simply we can say that here whatever the previous output of QS, same thing that is going to present. So whatever this QS variation is similar to NATH triggering of the clock. So whenever the NATH triggering like this, it is going to change its output. You can see clearly from this figure also. So these are the points that you always have to keep in your mind. And the variation of the output is very slow. The very slow means we are controlling the speed of this variation. So this is what we need to understand from this concept. We are going to study about the 4-bit SISO. SISO is called as a 4-bit SISO. So therefore, here SISO, basically you are going to see here, input, serial input and serial output. So 4-bit serial input and serial output. You can see clearly 4-bit serial input and serial output. So we are going to study this concept. So let me assume there are 4 flip flops. So 4 flip flops. 4-bit means 4 flip flops you have to consider. So these are D flip flops. So this is LSB and this is MSB. So D0, D1, T2, D3. So Q0, Q1, Q2, Q3. And this is Q0 bar, Q1 bar, Q2 bar, Q3 bar. So now I am going to give this as input. So this is Q3 has given input to D2. So Q2 has given input to D1. So Q1 has given input to D0. And this is the output that we are going to consider. See, all are given same clock. So this is called the synchronous. Synchronism means for all the flip flops we are going to give same clock. Then it is called the synchronism. So this is called synchronism clock. So for each and every flip flop we are going to give the same clock. So it is called as a synchronism. So now listen carefully. I am going to give the input in this fashion. So initially I am going to give, see basically this is the power stage triggering. So power stage triggering. Then I am going to give input in this fashion. 1, 0, 1, 1. And then I want to see how this input is passing from each and every aspect. So each and every aspect we have to see how it is varying inside we are going to see. So this is the clock. So I have drawn some vectorial representation. So this is the clock signal. Let me assume clock is having a frequency of f. Clock is having a frequency of f. So these are power stage triggering. So we have to give a power stage triggering like this. Under the power stage triggering I am keeping an arrow. So now listen carefully. Whenever I give a power stage triggering, so whenever I give a power stage triggering, this D3 is equal to initially we are going to give 1. So this input is going to pass through Q3. So therefore, let me assume initially it has Q3 is equal to 0. Means each and everything is initially Q3 is equal to 0, Q2 is equal to 0, Q1 is equal to 0, Q0 is equal to 0. When I give triggering, power stage triggering, then whatever the input occurs of D3, it is going to follow through Q3. So therefore, it is going to follow through Q3. Again, whenever I give a triggering, the next input is 0, so 0 is going to pass. Again, when I give a triggering, the next input is 1, so it is going to pass here. Again, if I give a triggering, the next input is 1, again it is going to pass through Q3. So 1, 0, 1, 1. So like this I am going to give. So for the first triggering, the input is 1. For the second triggering, the input is 0. For the third triggering, the input is 1. For the fourth triggering, the input is 1. So this is the output that we are going to get. Now, for this triggering, for this first triggering, whatever this output, Q3 input, see Q3 is given input to D2, so whatever this, it is going to flow through Q2. So now you can see, I already told you, so whatever, see at this triggering is given, so at this triggering is given, I already told you initially, so just before this system, what is the value? Q3 is equal to 0, so same thing it is going to happen. And as a triggering is happened, so whatever the previous input, just input is 1, so 1 is going to flow here. Again you give triggering, here it is 0, so 0 you are going to get. Again you give triggering, this just before this is 1, so you are going to get 1. Just before that you have to see. Similarly for Q1 you have to see the triggering. So at this process triggering you have to see what is the just the previous input of the Q2. So Q2 you have to see what is the state of that Q2. So just take given a triggering. So therefore Q2 here it is 0. So we are going to get 0 here. Again here also for triggering it is Q2 is equal to 0 just before this. So again same thing that we are going to get. Again here Q2 is equal to 1. So we are going to get 1 here. Again at this one, so Q2 is equal to 0. So we are going to get 0. Similarly for the last one Q0, for this process triggering, whatever the Q1 nature, just before the triggering, the output we are going to take it here. So therefore, for the process triggering, just before that it is 0. So 0 for here. Again triggering, just before that it is 0. So same thing. Just before the triggering, it is again 0. So same thing that we are going to get. Again before that it is 1. So we are going to get 1. So these are the output natures you are going to see. So initially, so we are going to get 0, 0, 0, 0, 1, 0, 0, 0, then 0, 1, 0, 0, next 1, 1, 1, 0, 1, 0, then 1, 1, 0, 1. Like this we are going to get. So listen carefully, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1. We are going to get in this format. So this is the clock that we are going to get for each and every triggering pulse. So what I am trying to tell you very simply, here whenever I give a clock, the power stage triggering, say whatever this whatever the input D3, it is going to flow through Q3. So whatever the input of D2, it is going to flow through Q2. So whatever the input of D1, it is going to flow through Q1. So whatever the input of D0, it is going to flow through Q0. So just before that instant, you have to see what is the nature of that. So if you do a triggering, you have to see just before that what is the nature of the Q3. So Q3's nature is going to flow through Q2. Similarly, just before the instant, you have to see what is the nature of Q2. It is going to flow through Q1. Similarly, just before this instant, you have to see what is the nature of Q1. It is going to flow through Q0. So like this, we are going to get these graphs. So now this is the pictorial graph. We need to draw in the tabular format. So you understand each and everything again. So same thing, but I am going to give you a tabular format. So listen carefully. So this is the clock signal. So this is the data that I want to send, which is 1, 0, 1, 1. So initially I am going to assume Q3, Q2, Q1, Q0, everything is 0. So now, then whenever the first triggering is happened, this one is came to here. So this 0 went to here, this 0 went to here, this 0 went to here. Second triggering, so whenever the second triggering, this 0 came to here, so 1 went to here, 0 went to here, 0 went to here. So the third triggering, this 1 went to here, this 0 went to here, this 1 went to here, this 0 went to here. On the fourth triggering, again, so 1 went to here, so 1 went to here, 0 went to here, so 1 went to here. So we can say same thing as to initially 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. So same thing I have already told you. This is the nature that we are going to get. So this is the point that you always have to keep in your mind. So we can say that, so this is the thing that you always have to keep in your mind. So we can say clearly, finally, we got all the inputs 1, 0, 1, 1. So 1, 0, 1, 1. See all the inputs now which are present in the outputs of Q0, Q1, Q2 and Q3. So this is the point that you always have to keep in your mind. All these inputs now are present in the outputs of Q0, Q1, Q2 and Q3. So listen carefully, this is the input I want to send up to here. So all this data I want to send up to here. So therefore, for the first triggering, 1 went to here, so 0 went to here, 0 went to here, 0 went to here. For the second triggering, 0 went to here, 1 went to here, 0 went to here, 0 went to here. For third triggering, 1 went to here, 0 went to here, 1 went to here, and 0 went to here. For fourth triggering, 1 went to here, 1 went to here, 0 went to here, 1 went to here. So therefore you can see all this 1, 0, 1, 1 has been in this presence 1, 0, 1, 1. All this one is present in the outputs of Q0, Q1, Q2 and Q3. So you can see clearly from this table. Same thing, same graph I already told you. The graph also same thing, which is 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1. See, one important point I will repeat again, you have to understand very, very important thing. See, whenever I give a positive triggering, B input is Q3, so B input is Q3. See, at that instant, just before that, you have to see what is the nature of Q3. That nature is going to pass through Q2. Similarly, for the positive triggering, B1 input is Q2. So just before that, what is the nature of the Q2 you have to see, that is going to flow through Q1. Similarly, at the positive triggering, B0 input is Q1. So just before that triggering, you have to see what is the nature of Q1, it is going to flow through Q0. So this is the point that you always have to keep in your mind. So like this. So all the data, input data 1, 0, 1, 0, 1, 0, 1, 1 is now present in the Q0, Q1, Q2 and Q3. So this is the point that you always have to keep in your mind. Let me tell you about the ring counter. This is a very important concept about the ring counter and the Johnson ring counter. So ring counter means very simple. So you can say this is the B flip-flop, B flip-flop, B flip-flop and B flip-flop. Let me assume this is the 4 bits are there. So this is there B0, B1, B2, B3. So Q0, Q1, Q2, Q3. This is Q1 bar, Q1 bar, Q2 bar and Q3 bar. So I have given input like this. So Q3 input is given to B, Q2 input is given to B, Q1 input is given to like B0. So now I have taken a feedback from Q0. From Q0 I am taking a feedback and I have given to here. So from Q0 if I take a feedback and I give to this is B, and all these are same clock with synchronism, because all are going to trigger at a same instant of time. So this called as a, we can say synchronism. Let me assume the clock frequency is equal to AF. Then listen carefully, very important point. The circuit is called as the whenever the output of Q0, it is given as input of B, it is called as the ring counter, and each having a frequency of f by 4. See, all these outputs will have a frequency of f by 4. If there are 4 flip-flops, right, so therefore the frequency will be f by 4. If there are n flip-flops, you will get f by n at each and every output. At each and every output, we are going to get the same frequency. As there are 4 flip-flops, we are going to get f by 4. If there are n flip-flops, we are going to get f by n. So this is a very important point that you always have to keep in your mind. If there are n flip-flop means the output of each flip-flop will have f by n. If there are 4 flip-flops means the frequency is f by 4. So this is called as the ring counter. Now let me tell you about the Johnson's ring counter. Johnson's ring counter means if you take feedback from Q0 bar, if you go to D, it is called as the Johnson's ring counter. So this is the Johnson's ring counter. So listen carefully. So therefore we can say that. So this is basically an only to only this is a D0, D1, D2, D3, Q0, Q1, Q2, Q3. This is Q1 bar, Q1 bar, Q2 bar, Q3 bar. So Q3 is given input to D2 and Q2 is given input to D1 and Q is given input to D0. So if you take feedback from Q0 bar to D, if you take feedback from Q0 bar to D, it is called as a Johnson's ring counter. If I take feedback from Q0 bar to D, it is called as a Johnson's ring counter, and you can see all are giving the clock at the same instant. So it is called synchronism of clock. Then it is called the Johnson's ring counter. It is called as a Johnson's ring counter. If you take feedback from Q0 and if you go to D, it is called the ring counter. If you take feedback from Q0 bar and if you give input to D, it is called the Johnson's ring counter. It's a very important point. If you take feedback from Q0 and if you give back to D, it is called as a ring counter. But if you take feedback from Q0 bar and if you give to D, it is called as a Johnson's ring counter. Suppose if you are not giving feedback, this is the circuit that we are going to get. If you give feedback from Q0 to D, it is called as the ring counter. If you give feedback from Q0 bar to D, it is called Johnson's ring counter. Suppose if you are not going to give any feedback, this the circuit that we are already studying. If you are taking feedback from Q0 and if you give to D, it is called as a ring counter. If you take feedback from Q0 bar and if you give to D, it is called as the Johnson's ring counter. So we will discuss about these two concepts again also in a very detailed manner. We are going to discuss about the 4-bit serial input parallel output register. So now we are going to discuss about the 4-bit serial input parallel output register. So you can see clearly these are the 4 flip-flops. I am going to give clock at each and every flip-flop has the same amount of clock. So it is called as synchronous clock, because for each and every, for all the flip-flops we are going to trigger at the same time. So it is called as a synchronous clock. So therefore now you can see clearly. So now this is a D0 Q0, D1 Q1, D2 Q2, D3 Q3. So input we are going to give serial fashion and we are taking output from the parallel fashion. So it is called as the serial input and parallel output, because we are giving input serially and we are taking output parallelly. So it is called as the serial input and parallel output. So this is the point that you always have to keep in your mind. So we are going to give the input serially and we are taking output parallelly. So it is called as the serial input and parallel output registers. So therefore serial input and parallel output. So this is the concept regarding the small diagram regarding the serial input and parallel output. Because we are basically giving the input in a sequential manner, in a serial manner. But here the output is taken in the parallel fashion. So it is called as a serial input and parallel output. And each and every flip-flop has the clock, same clock, and we are triggering at the same instant. So it is called synchronous clock. So now another concept, which is 4-bit parallel input and parallel output register. So basically we are going to give it is a 4-bit parallel input and parallel output. Means the input we are going to give parallel and the output also we are taking parallel. So it is called as the parallel input and parallel output register. So you can see clearly there are 4 flip-flops. Each is representing 1 bit. So this is a D0 Q0, D1 Q1, D2 Q2 and D3 Q3. This is Q0 bar, Q1 bar, Q2 bar and Q3 bar. So we are going to give a positive triggering clock for each and every flip-flop. So for each and every flip-flop we are going to give the positive triggering. So this is called as the clock. So this is basically a clock signal. So for each and every flip-flop, we are going to give the same clock. At the same instant, we are triggering each and every flip-flop. So it is called synchronous of clock, so synchronous clock. So now we can see we are going to give input. For each and every flip-flop, we are going to give the input in a parallel fashion, and we are taking the output also in the parallel fashion. So because of this reason, it is called as the parallel input and parallel output, because we are giving the input parallelly and taking the output parallelly. So it is called as the parallel input and parallel output. So this is the point that you always have to keep in mind. So the circuit is needing a parallel input and parallel output. So now we will discuss about the 4-bit parallel input and serial output register. So this is the last concept regarding these operations, the 4-bit and parallel input and serial output register. So you can see clearly these are the 4 flip-flops we have taken. Each flip-flop is representing 1 bit. So this is the D0 Q0, D1 Q1, D2 Q2, D3 Q3. This is Q1 bar, Q1 bar, Q2 bar and Q3 bar. So now here for each and every flip-flop we are giving the same clock. Positive is triggering for each and every flip-flop we are going to give any synchronous manner. Means each and every flip-flop is activated at the same instant. So this is called the synchronism of clock. So now here parallel input means we are going to give input in a parallel fashion, and we are output is traveling in a serial fashion. So you can see we are going to give the input in a parallel fashion, and we are going to take the output in a serial fashion. So you can see clearly there is a 2 cross 1 mux is there. Here also 2 cross 1 mux is there. Here also 2 cross 1 mux, which 2 inputs and 1 output. 2 inputs and 1 output. 2 inputs and 1 output. Here the control signal, all the control signals for all the multiplexer, 2D cross multiplexer, then one control signal, all this we are going to connect together and call this as the control signal. So if control is equal to 0, if control is equal to 0 means I0 is activated. So whenever I0 is activated means all the parallel inputs are going to transfer. All the parallel inputs are given. So therefore loading input to register. So therefore inputs are going to get registered to the loading the input to register. Since inputs are going to register into this one. So loading inputs to the register. Suppose if you keep control is equal to 1, what is going to happen? If you keep control is equal to 1 means I1s are going to get activated. So this outputs means Q3 is going to transfer. So Q3 is going to get transferred. So therefore outputs are going to get transferred from one flip-flop to the other flip-flop in a serial fashion. So therefore we can say, so doing serial output or shifting data to the right side. So therefore doing serial output or shifting data to the right side. So output is traveling in a series fashion from left side to right side. You can see clearly. So this called as the doing serial output or shifting data to right side. So simply we can say whenever the control signal is equal to 0 means loading input to register, and whenever the control is equal to 1 means doing serial output or shifting data to the right side. So this is the basic agenda of this one, 4-bit parallel input and serial output. So we are going to give parallel input like this manner and taking serial input. So whenever the control is equal to 0, all the inputs are going to move into the register, and whenever the control is equal to 1, all the outputs are going to transfer in a serial manner. So this is the point that you always have to keep in your mind. So whenever the control is equal to 0 means loading the inputs to the registers, and whenever the control is equal to 1 means doing the serial output or shifting the data to the right hand side. So these are the points that you always have to keep in your mind. Now let me give the summary of each and everything that we have studied. So therefore for n-bit register, minimum clock pulse required for n-bit. So that listen carefully, for n-bit register minimum clock pulse is required for n-bit to transfer. So listen carefully, for single input serial output, serial input parallel output, parallel input serial output, parallel input and parallel output. So this is a very important point. So we have to see we can say the number of clock pulses are required to transfer the n number of bits. So for n-bit register, minimum clock pulse, the minimum number of clock pulses required for n-bit to transfer. So listen carefully here, for n-bit register, the minimum number of clock pulses required for n-bit to transfer. See, whenever there is a serial input, I already told you, if you want to transfer the serial input, we need n number of clock pulses to transfer n number of bit. I already told you, serial input means I already told you, we need n number of clock pulses. We need n number of clock pulses to transfer the data. So n number of clock pulses are required to transfer the n bit. Similarly, serial output means already one we are going to get, so then we are going to get n minus 1. So n minus 1 clock pulses are required to get the serial output. Whereas parallel output means only one clock pulse is required. Whereas parallel output means 0 because directly we are going to get, so no need of clock pulse. So this is the easy way to remember. So various serial input is there, just keep your n. Serial output means n minus 1, parallel input means 1, parallel output means 0. So here input side and output side. So serial input and serial output means n minus 1. Here serial input means n, parallel output means 0. Parallel input means 1, serial output means n minus 1. Parallel input means 1, parallel output means 0. So this is the input side and this is the output side. So this is the way, if you understood this concept, you can substitute wherever the input is there, substitute these things as per the condition. So it is an easy way to remember. So listen carefully. For n bit register, the minimum number of clock pulses, required to transfer n bit. So therefore, for n bit register, the minimum number of clock pulses required to transfer n bit data. If serial input means we need n number of pulses. We need n number of pulses to transfer the n bit data to the n bit register. For serial output means we need n minus 1 clock pulses required to take out that serial data. N minus 1 number of clock pulses are required to take that data serially output. For parallel input we require 1 clock pulse in order to feed all the inputs. Whereas for parallel output means we don't need any pulse because automatically outputs are present, so we can take it directly. So it is 0. So listen carefully. If you want the n bit data to store in the n bit registers in the serial input, it requires n number of clock pulses. Whereas for serial output to take only n minus 1 clock pulses. Whereas for parallel input means we require only 1 clock pulse. Whereas for parallel output we require only 0 pulse. So you can see clearly for input side and output side. So whenever serial input means n, serial output means n minus 1. Serial input means n, parallel output means 0. Parallel input means 1, serial output means n minus 1. Parallel input means 1, parallel output means 0. So this is the point that you always have to remember. So listen carefully. N number of clock pulses are required to transfer the n bit data through serial input, and we require n minus 1 clock pulses to take out the data serially output. And we require n number of clock pulses to send the data through serial input, and we require 0 number of clock pulses to take the data by parallel output. And we require 1 clock pulse to feed the data through parallel input, and we require n minus 1 clock pulses to take the data serially output. And we require 1 clock pulse required to feed the n bit data through parallel input, and we require 0 clock pulses to take the n bit data in the parallel output. So this is the point that you always have to keep in your mind. So finally I can say, for n bit register, the minimum number of clock pulses required for n bit transfer is this, the table that you always have to keep in your mind. So now I will discuss about the 3-bit ripple counter. 3-bit ripple counter, especially for this 3-bit ripple counter is basically it is a up counter. So this 3-bit ripple counter is basically up counter we are going to study. So you can see clearly. So this is a 3-bit ripple counter. Ripple counter means one important point here. See, one important point here. Output of one flip-flop is given as clock to the other. So listen carefully. So ripple counter means output of one flip-flop. If you give in as a clock, it is called as the ripple counter. So listen carefully. If the output of one flip-flop is given as clock to the other flip-flop, it is called as the ripple counter. So therefore, 3 bits means we need 3 flip-flops. So 3 flip-flops. So ripple as is J0, K0, J1, K1, J2, K2. Q0, Q0 bar, Q1, Q1 bar, Q2, Q2 bar. So now, this is, I am going to keep all these things at the one condition. So J is equal to 1, K is equal to 1 means these are in the toggling condition, or simply we can say these are in the toggling condition or raise and 1 condition. So 1, 1 and 1, 1. So now, let me initially clock pulse having a frequency of f. See, whenever, listen carefully, in the ripple counters, whichever the clock which is given initially, it is that flip-flop is called as the LSB, and the last one is called as the MSB. It's a very important point. In the ripple counters, the clock which is given initially to a flip-flop is called as the LSB, and and the final flip-flop is called as the MSB. It's a very important point that you always have to keep in your mind. So whichever the clock it is given initially to a clock, to a flip-flop, it is called as the MSB, and the last one is called as the MSB. And here output of one flip-flop is given as a clock to the other flip-flop. As you can see, these are the negative edge triggering. So if it is a frequency f means it is f by 2, and f by 4 and f by 8, because each flip-flop has two states. So f by 2, and here f by 2 by 2 is nothing but f by 4, and f by 4 by 2 is nothing but f by 8. So this is the point that you always have to keep in your mind. So therefore the output frequency of this MSB, the output frequency of this MSB having an output frequency of f by 8, because each flip-flop has two states, so we have to divide by 2. So therefore, if this is the f means f by 2, f by 2 by 2 is nothing but f by 4, and f by 4 by 2 is nothing but f by 8. So this is the point that you always have to keep in your mind. So general expression is f by 2 to the power of n. N is nothing but number of flip-flops. As there are 3 flip-flops, so 2 cube is nothing but 8, so f by 8 frequency. So like this that you have to remember. So now we will discuss the figures also in a very easier manner. Let me assume this is the clock. So clock is nothing but this is the graph we are going to get the clock. All these are negative edge triggering. So negative edge triggering. So whenever, if you listen carefully, whenever there is a negative edge triggering here, this output is going to get changed from 0 to 1 and 1 to 0, because this is in the toggling condition. So you can see create initial and going to assume create is equal to 0. So whenever negative triggering happen, it is changed to 1. Negative triggering means again changed to 0. Negative triggering means again changed to 1. Negative triggering means again changed to 0. So 0 to 1, 1 to 0. But this Q0 is given input to this flip-flop. So therefore, this Q1 is going to get changed. This Q1 is going to get changed only whenever the Q0 is changing from 1 to 0. So whenever the Q0 is changing from 1 to 0, then only Q1 is going to get changed. So listen carefully. So Q0 is changing from 1 to 0 here, 1 to 0 here. At these conditions only, the Q1 is going to get changed. Initially I am going to assume this is 0. So up to it is 0. When it is a negative edge triggering, again it will change. When it is a negative edge triggering, again it will change. Similarly, Q2 will change only whenever the Q1 is changing from 1 to 0, negative edge triggering. So whenever Q1 is changing from 1 to 0, then only Q2 is going to get changed. So Q1 is changing from 1 to 0 at this condition only. So up to that time it is going to be a 0 state only, but after that it is going to change to 1 because it is a toggling condition. So this is the point that you always have to keep in your mind. So whenever clock is changing from 1 to 0, then Q0 is going to get changed. Whenever the Q0 is changing from 1 to 0, then only Q1 is going to get changed. Whenever Q1 is changing from 1 to 0, then only Q2 is going to get changed. So this is a point that you always have to keep in mind, because these are all negative edge triggering. So listen carefully. Whenever the clock is changing from 1 to 0, then only Q0 is going to get changed. And whenever the Q0 is changing from 1 to 0, then only Q1 is going to get changed. Similarly, whenever the Q1 is changing from 1 to 0, then only Q2 is going to get changed. So this is by this concept I have drawn all these things. So within this concept only I have drawn these things. So these are the graphs that we are going to get. See, now I want to draw in the tabular format, but not previously I draw in the pictorial format. So now I want to draw in the terms of the tabular format. You can listen carefully. I already told you the important point. Q1 is going to get changed. So Q1 changes only whenever the Q0 is changing from 1 to 0. I already told this point. So Q1 changes if Q0 changes from 1 to 0. Similarly, Q2 changes. So Q2 changes only when Q1 is changing from 1 to 0. So Q2 changes if Q1 is changing from 1 to 0. And I already told you Q0 changes. So Q0 changes whenever the clock is changing from 1 to 0. All these things I already told you. So Q0 changes when the clock is changing from 1 to 0. Similarly, Q1 changes if Q1 is changing from 1 to 0. Similarly, Q2 changes if Q1 is varying from 1 to 0. All these things I already told you. So let me assume initially. So all this Q2, Q1 and Q2, Q1 and Q0. Q0 is always MSB and this Q2 is the MSB. So MSB. So whatever the clock which is given to the flip-flop is called as MSB and the farthest one is called as the MSB. So this is MSB and this is MSB. Q2, Q1, Q0. So initially when there is no clock, I already told you, when there is no clock all are having a 0 values. But when the clock is, one clock means first stage triggering occurred. First stage triggering occurred, I already told you, then Q0 is going to change from 0 to 1. So Q0 is changing from 0 to 1. Then see, Q1 changes only when Q0 changes from 1 to 0, but there is no change, so here also 0. Q2 changes only when if Q1 changes from 1 to 0, so here is only 0 only, so here also 0. But second clock triggering, again it will change from 1 to 0. So you can listen carefully. I already told you, Q1 changes whenever Q0 changes from 1 to 0, yes, when you change from 1 to 0, so it is going to get changed. But here it is same as the previous one. For the third triggering, I already told you, it will always change from 0 to 1 again. It will be same as the previous one, and also same as the previous one because it is again 1 only. For the fourth triggering, it will change to 1 to 0. So you can see this is also 0 because Q1 changes only when Q0 changes from 1 to 0. Q1 changes only when Q0 changes from 1 to 0. Yes, it is changed from 1 to 0. So as there is a change, so it is going to get change here. Similarly, I already told you that Q2 changes only when Q1 changes from 1 to 0. Yes, it is changed from 0 to 1 here. Similarly, for the fifth triggering, so this always changes from 0 to 1. So here it will be same as the 0, here will be same as the 1. Again sixth triggering, so 1 to 0. So when you does 1 to 0 means it will change. Again 0 to 1, so same thing will be present here. For the seventh triggering, 0 to 1, same thing here, same thing here. For the eighth one, so it is changing from 1 to 0, yes, it will change. Again 1 to 0, yes, it will change. So this is the tabular format that we are going to get. So you can see clearly, this is the decimal format is 0, decimal format is 1, decimal format is 2, decimal format is 3, 4, 5, 6, 7. So we can see clearly we are going to from 0 to 7 and we are going to give us back to this one. Again it will repeat. So you can see clearly it is reading from 0 to 8, 0 to 7. Again it is going back to the 0. So you can see it is called as the up counter because it is reading from 0, 1, 2, 3, 4, 5, 6, 7. Again it is going back to 0, 1, 2, 3, 4, 5, 6, 7. Because the up counter means it is reading from 0 to 7 and going back. So this is called as the up counter. It is basically an up counter. So this is the point that you always have to keep in your mind. So Q0 always changes from 0 to 1, 0 to 1, 0 to 1. Always it is going to change from 0 to 1, 1 to 0, 0 to 1, 1 to 0 like this. But Q1 changes. But Q1 changes only when Q1 changes only when Q0 changes from 1 to 0 and the Q2 changes only when Q1 changes from 1 to 0. So this is the concept that you always have to apply. Let me assume here it is say 0 to 1. See, it has to change 1 to 0, otherwise it will be same as the previous state. 1 to 0, yes, so it will change. It is same thing here. Again, there is 0 to 1, same output, same output. 1 to 0, yes, change. So it also output will change 1 to 0. 1 to 0 means yes, is occurred, so it is also changing its output. Again 0 to 1, same thing will be there, same thing will be there. And here 1 to 0, yes, it is going to get changed. So also it is going to get changed. But here it is made 1 to 0, then it is going to change, otherwise previous state 1. Similarly 0 to 1, so again it is going to become same 1 as previous and previous minus 1. So now it is changing from 1 to 0. So 1 to 0 means it is changing from 1 to 0 means this will change, and also 1 to 0 means this will also change. So you have to draw this figure like this. So you can say this is what it is going to repeat from 0 to 7 is repeating and going back to 0. So this is called the up counter. So this is the important point that you always have to keep in your mind. So therefore simply we can say that this is said to be up counter because it is reading 0, 1, 2, 3, 4, 5, 6, 7, and then 0, 1, 2, 3, 4, 5, 6, 7. So always finally I am trying to tell you a very important point. So Q1 changes only when Q0 changes from 1 to 0 and Q2 changes only when Q1 changes from 1 to 0. So from this we have drawn this table, and whatever the clock which is directly given to the flip-flop is called as LSB, and the formation is called as the MSB. So based on this, I have drawn this one, and also ripple counter means the output of 1 is going to give us the clock to the other flip-flop, so it is called the ripple counter. Here the data is going from 0 to 8, 7 and back to 0, it is called as the up counter, means reading the data from 0 to 7. So for n-bit ripple counter, very important point, you have to always keep in your mind, for n-bit ripple counter always, the T clock should be always greater than n times the propagation delay of the flip-flop, because n-bit flip-flop means n-bit ripple counter means all are in the series fashion, so all are in the series fashion because output of one is given as a clock to the other. So therefore, because of this, the overall clock period should be always greater than n times the propagation delay of the each flip-flop. As there are n flip-flops, so we have to consider n because we are going to assume all are identical. So the clock period should be always greater than n times the propagation delay of the flip-flop for n-bit ripple counter. So what is the frequency? T clock is nothing but 1 by f. So 1 by f is nothing but 1 by f. Clock frequency is lesser than 1 by NTPD FF. So the maximum clock frequency is nothing but here 1 by n into the propagation delay of the flip-flop. So this is the point that you always have to keep in your mind. So the clock period, the time clock period is always greater than n times the propagation delay of the flip-flop, and the T clock is nothing but 1 by f clock. So if you solve this one, we are going to get f clock is lesser than the 1 by n times of propagation delay of the flip-flop. So the clock frequency also is equal to 1 by n times of the propagation delay of the flip-flop. If this is minimum, we are going to get this as the maximum. If the propagation delay of the flip-flop is minimum, we are going to get the maximum clock frequency. So this is the point that you always have to keep in your mind. So in the n-bit ripple counter, always the clock pointer should be always greater than the n times the propagation delay of the flip-flop. So replace T clock by 1 by f clock, again we are going to get. So f clock is lesser than 1 by n times the propagation delay of the flip-flop. So maximum clock frequency is equal to 1 by n times propagation delay of the flip-flop. If propagation delay of the flip-flop is minimum, then we are going to get the clock frequency as maximum in the n-bit ripple counter. So because with the n-bit ripple counter, as output of one flip-flop is given as a clock for the other flip-flop, so it has to travel from one flip-flop to other flip-flop in a sequential manner. So because of this only, the clock should be always greater than n times the propagation delay of the flip-flop. So based on this, we are going to get the maximum clock frequency is equal to 1 by n times the propagation delay of the flip-flop. Now we are going to study about the 3-bit ripple down counter. Previously we have learned about the basically 3-bit ripple counter, basically the up counter, but now we are going to study about the 3-bit ripple down counter. So you can see clearly same thing. It was JK flip-flop with K is J is equal to 1, K is equal to 1. We are going to replace by T flip-flop, and now the performance is same because both are having the same thing. So therefore it is also JK, you can replace JK flip-flop or T flip-flop with the input is equal to 1. Both are same. So therefore it is they all are going to work in the toggling condition mode. All are working in the toggling condition mode. So all it will be whenever the clock that they are going to give to the first flip-flop, that is called as the LSB, and the furthest one is called as the MSB. So now this is T0, T1, T2. So Q0, Q1, Q2. This is Q0 bar, Q1 bar, Q2 bar. And already told you the output of one flip-flop is given as a clock to the other flip-flop. The output of one flip-flop is given as clock to the other flip-flop. And these are not post-stage triggering. These are post-stage triggering. So now all the T's are at even because they are working in the toggling condition, and this is the LSB and this is the MSB. And already told you the clock frequency is F, then the frequency of this is, it has two states, so F by 2. It is also has two states, so input by again 2, which is F by 2 by 2 is nothing but F by 4. And it also has two states, again by frequency by 2, which is F by 4 by 2 is nothing but F by 8. So what I told you the general formula, which is the F by 2 to the power of n. The farthest for MSB, the frequency, the output frequency is equal to F by 2 to the power of n, where n is the number of flip-flops are present. So this is the, so you can see clearly, ripple means output of one is given as a clock to the other one. So this is called the ripple counter. But basically down counter means it is reading from high to low. We will discuss regarding this one. So now I am going to draw the graphs, see clearly. So this is the clock signal I have drawn. So this is the clock signal. See basically these are the post-stage triggering means arrow upward. So arrow upward we have to draw the positive triggering. Then see Q0 is going to get changed. So Q0 is going to get changed only whenever the clock speed is having a positive means whenever the clock speed varies from 0 to 1, then this Q0 is going to get changed. Similarly, Q1 is going to get changed whenever the Q0 changes from 0 to 1. Similarly, Q2 changes whenever Q1 changes from 0 to 1. So this is a very important point. See, Q0 changes whenever the clock signal changes from 0 to 1, and Q1 changes whenever the Q0 changes from 0 to 1. Similarly, Q2 changes whenever the Q1 changes from 0 to 1. So this is a point that you always have to keep in your mind. So therefore, here clock is changing from 0 to 1, positive is triggering. So Q0 is going to get changed here from 0 to 1. Again, here also it is going to get changed. Again clock is changing from 0 to 1, so again output is going to get changed. Again clock is changing from 0 to 1, so again output is going to get changed. Again clock is changing from 0 to 1, again output is going to get changed. So this is the graph that we are going to get. Similarly, Q1 is going to get changed only when Q0 changes from 0 to 1. This positive is triggering. So this is the positive is triggering, positive is triggering, and positive is triggering. At this instance only, Q1 is going to get varied. So here 0 to 1, again 1 to 0, again 0 to 1. Similarly, Q2 varies only when Q1 changes from 0 to 1. So therefore Q2 changes only when Q1 changes from 0 to 1. So therefore you can see clearly so here Q1 changes from 0 to 1 here, and here also it is going to change from 0 to 1. So at these two instances only the output Q1 is going to get changed. So it is changing from 0 to 1 here, again 1 to 0 here. So these are the graphs that we are going to get. So these are the graphs that we are going to get for Q0, Q1 and Q2. So Q2 is always the MSB and Q8 is always the LSB. So this is the point that you always have to keep in your mind. See Q value changing from 0 to 1, 0 to 1. Whenever the clock is changing from 0 to 1. So Q1 changes whenever the Q1 changes from 0 to 1, and Q2 changes whenever the Q1 changes from 0 to 1. So with this concept, this is the pictorial graph, but now we will discuss about the tabular format also. As I already told you, Q1 changes. So I already told you, Q1 changes when Q1 changes from 0 to 1, and Q2 changes when Q1 changes from 0 to 1. So same thing I have written. Q1 changes if Q1 changes from 0 to 1, and Q2 changes if Q1 changes from 0 to 1. So now with the help of this concept, now we are going to draw this tabular format. So initially I am going to assume all are 0. Initially I am going to assume all are at 0. See, whenever the first clock is given, the positive is triggering. So Q0 is changing from 0 to 1. So whenever Q0 is changing from 0 to 1, which is changing, Q1 is changing, so 0 to 1. If Q1 is changing from 0 to 1, which is changing again, Q2 is also changing, 0 to 1. Similarly again it will change from 1 to 0. So always Q2 is going to change in a continuous manner. So now we are changing from 1 to 0, so there is no change here. 1 to 1 means again no change here. Similarly 0 to 1, again it is going to get changed. So Q1 changes only when Q1 changes from 0 to 1, yes, the change is there, but here it will never change. Again 1 to 0, it will never change, it will never change. Again 0 to 1, yes, it will change, this one will change. Again 0 to 1, again this will change. 1 to 0, so no change here. 1 to 1, no change here. 0 to 1, yes, it will change from 1 to 0. So therefore 1 to 0 means there is no change here. So 1 to 0 means again there is no change here, so no change here. So you can see clearly this is 8, 7, 6. So this is 7, 6, 5, 4, 3, 2, 1, 0. So this is reading from high to low level. Again 0, 8, 0, 7, 6, 5, 4, 3, 2, 1, 0. It is repeating in this fashion. So it is always repeating in this fashion for all the time. So it is called as a down counter because it is reading from 7, 6, 5, 4, 3, 2, 1, 0 like this. So it is called the down counter. So that is the reason it is called as the down counter. So this is a point that you always have to keep in your mind. So finally I can say that the Q1 is changing only when Q0 changes from 0 to 1, and Q2 changes only when Q1 changes from 0 to 1. So with this concept we have to understand. So we have to draw this table based on this concept only. So now we will discuss about the modify ripple up counter. So modify ripple up counter means, see what is this mod number? Mod number indicates that the number of unique states in the output. The number of unique states in the output, it is going to give you a mod number. Mod number means the number of states, the number of unique states that are going to present in the output, that is called as the mod number. Listen carefully. Mod is nothing but it is going to give you the number of unique states in the output, that is called as the mod number. So now we are going to discuss about the modify ripple up counter. Modify ripple up counter means we are going from 0, 1, 2, 3, 4 like that. It's a ripple up counter. So now we are going to design this modify ripple up counter means it should have only 5 unique states. It should have only 5 unique states. So now see clearly, we are going to design the circuit. As I already told you, whether you can use T flip-flop or JK flip-flop, it's a ripple up counter means, ripple means always you have to understand. Ripple means very simple, always the output of one flip-flop is given as a clock for the other flip-flop. This is the basic thing that you always have to understand. And the clock which is given the first flip-flop, it is always LSB, and the furthest one is always LSB. So this is J0, K0, J1, K1, J2, K2. We are using basically only 3 flip-flops, only 3 bit we are going to choose here. So it's a 1, 1, 1, 1 and 1, 1. So Q0, Q0 bar, Q1, Q1 bar, Q2, Q2 bar. So now output of this is given as a clock to the other one. So output of this is given as a clock to the other one. So these are basically negative edge triggering. So these are the negative edge triggering, because in the negative edge triggering only we have discussed it is a up counter. In the positive edge triggering it has become a down counter. Just now we have seen. So in the negative edge triggering it is a up counter, and in the positive edge triggering it is a down counter. And I will discuss these details also, how to remember these things, up counter, down counter, and we will discuss in the coming days, or we can say coming lectures I will discuss these concepts. But up to now remember that whenever there is a negative edge triggering means it is a up counter, and positive edge triggering means it is a down counter. So now here I want to make this as the modify means 5 states. I want to make this one. So how to design the circuit, I will give you information. So before that, just draw this diagram. So now based on this I am going to draw this one. Very important point here. See, so now listen carefully. See, it's a modify counter, right? It's a modify ripple up counter means whatever the output frequency is f by mod number. So if it's a plot of the frequency of f, then the NSB, the output frequency is equal to the clock frequency by the mod number. Mod number is 5. So this is always equal to f by 5. It's an important point. So now listen, I want to go for the modify ripple counter. Modify ripple counter means ripple up counter means 0, 1, 2, 3, 4. So these are the 5 states. So whenever this 5 number comes, so 0, 1, 2, 3, 4. So whenever 5 comes, whenever 5 means the decimal number is 5 means the binary format is 101. So whenever it is going to come, again it has to go back to the 0. Listen carefully. So 0, 1, 2, 3, 4. These are the 5 unique states. So whenever the decimal number 5 means 101, whenever it is going to come, then we have to switch back to the again starting with this 0, 0, 0. So like that means we have to go for this AND gate. So with the help of this GAN gate, so 1, 0, 1 is nothing but Q2 should be equal to 1, and Q2 is equal to 1, and Q1 is equal to 0. So Q1 is equal to 0 means here, I want to tell you, so we have to take from here Q1 bar, and this is Q0. So listen carefully, I want to tell you, see 1, 0, 1 is nothing but, you simply can write like this, like written Q2, Q1 bar, Q0. So Q2, Q1 bar and Q0. So Q2, Q1 bar and Q0. So we have taken through this and we have kept a AND gate. So this output we have given to the clear part. So clear, this is called the clear signal. So clear signal we are going to give. So whenever the clear has become activated means by default outputs, all the outputs are going to become 0. So listen carefully. Whenever this clear part is activated, we can say this CLR. Whenever this clear part is activated means all these outputs are going to become by default 0. So all these outputs are going to become by default 0. So I wanted to not for ripple counting means it is going to read from 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4 are nothing but 5 unique states. So whenever the decimal number 5 is nothing but 101. Whenever it is going to come, we have to activate the clear signal. Whenever this clear signal is activated, all these things are going to become 0. Again it is going to read it from 0. It's 0, 1, 2, 3, 4. And then whenever the 5 comes, again it is going to become 0. Again it is going to get repeat to 0, 1, 2, 3, 4 like that. So total 5 unique states are there. So that is the reason it is called as the modified ripple up counter. Because it is reading from 0, 1, 2, 3, 4. Again 0, 1, 2, 3, 4. So it is called as the ripple up counter with the unique states of 5. So it is called as the modified counter. So now we are going to discuss how it is going to perform. So I wanted to tell you this is called as LSB and this is called as the MSB. So which are the clock which is given to the initial flip-flop is called as LSB and the formation is called as the MSB. So Q2, Q1, Q0. So now clear signal I wanted to tell you the clear output is nothing but which is I wanted to tell you Q2, Q1 bar and Q0. So Q2, Q1 bar and Q0. So now initially when there is no clock signal I wanted to tell you all are going to have a initially 0, 0, 0. As I wanted to tell you one important point here, Q1 is going to get varying. So Q1 varies only when Q0 changes from 1 to 0. And similarly, Q2 varies only when Q1 changes from 1 to 0. So these things I want to tell you because these are the variables triggering. So as Q2 changes from 0 to 1. So there is no change here, there is no change here. When Q0 is changing from 1 to 0, when which is changing, Q1 is changing 0 to 1. So there is no change here. Again 0 to 1. So no change here, no change here. Suppose 1 is changing to 0. Then there is a change here. Again when 1 is changing to 0 means again there is a change here. And next step is we can default we are going to get a transient state. It is called as the 0 to 1. So 0 to 1 is same here. 0 to 0 here also 1. So this is called as the transient state. So whenever this is become active, whenever this is nothing but Q2, Q1 bar, Q0. Whenever this was active, so this clear signal will be activated. In the remaining cases, the clear signal is 0. So nothing is going to get happen. When the clear was activated, when the clear signal was activated, all the flip-flops by default order will become 0, 0, 0. And then it is going to get repeated from here. So if you count 1, 2, 3, 4, 5, there are 5 unique states. Whenever the sixth state came, it is called as a transient state. For a small amount of time it is going to present and the clear signal is going to get activated and we are going to get to the 0, 0, 0. Again the starting state we are going to get. You can see clearly it is the up counter because 0, 1, 2, 3, 4 and it is the up counter and it has 5 unique states. So because of this reason it is called as the modified counter and this is called the transient state. This is called as a transient state. It is not a stable state, it is a transient state. So whenever this transient state came, the clear signal was activated. So therefore we are going back to the again 0, 0, 0. So this is the important part that you always have to keep in the mind. So we have 5 stable states and 1 transient state. Whenever this transient state is activated, the clear is activated and we are going back to the 0, 0, 0. Again it is going to repeat from here. So it's like a loop. We are basically in a loop. Suppose by replace negative edge triggering by positive edge triggering. Suppose here I am going to replace the negative edge triggering by positive edge triggering. Then what it is going to perform? We will see. So now listen carefully. Suppose if you are going to replace the negative edge triggering by positive edge triggering, then what is the graph that we are going to get? What is the table that we are going to get? Listen carefully. Initially I am going to assume it is 0, 0, 0. So now this this is basically this is Q0, Q1 and Q2. See, basically this is Q0, Q1, Q2. So I have written wrong here. Actually this is Q0, Q1, Q2 and this is Q0, Q1 bar, Q2. But anyway the concept is same. So this is actually Q0, Q1, Q2 and this is Q0, Q1 bar and this is Q2. So this is Q2, Q1, Q0. Here signal is equal to Q2, Q2 Q0 because 101. I already told you 101. Whenever 101 came, this is going to get activated. So now, if I am going to replace the negative is triggering with positive is triggering, and what is going to happen? We can see clearly initially all the things are 0, 0, 0. So it is going to go from 0 to 1. So we know 0 to 1 means yes, positive is triggering. So therefore it is going to get changed. Again 0 to 1, it is also going to get changed. So now 1 to 0. So there is no change here. There is no change here. Again 0 to 1. So 0 to 1 means again it is going to get changed. So 1 to 0 means there is no change here. So this is called as 101. So this clear signal is going to get activated. In the remaining cases the clear signal is not activated. So this is the transient state, and then by default all the things are going to become 0, and then we are going back to the starting one. So we are going to loop. So now only three things, this state, this state, this state. Only these are the three unique states we are going to get, and the transient state. So this is called as the mod 3 counter. So therefore the circuit now is going to act like a mod 3 counter, and I already told you what is the frequency of the MSB bit is equal to supply frequency by mod number, which is 3. So this is the point that one is going to remember. So therefore if you go for the positive triggering, it is going to act like a mod 3 counter, and the frequency of the MSB bit is equal to supply frequency by mod number, which is 3. So therefore it is going to act like a mod 3 counter. So always this is the point that you always have to keep in your mind. So this is the thing that we are going to get. Whenever the clear signal is equal to 0 means it is going to perform normally. Whenever the clear signal is going to get activated, then by default all the outputs are going to become 0, and then we are going in a loop. Only these three are the stable states, and this is called the transient state. So this is the point that you always have to keep in your mind. So the circuit is now going to act like a mod 3 counter, and the frequency of the MSB bit Q2 is equal to supply frequency by mod number, which is 3 here. Now we are going to learn about the other concept is called as the synchronous series carry up counter for 4 bit. So up to now we are learned about the up counter and down counter in the case of the ripple counters. Means the output of one flip flop is given as the clock for the other flip flop, like that we have discussed. But now this is the synchronous series carry up counter for 4 bit. Means synchronous means basically the clock pulse is same for each and every flip flop. So you can see the clock pulse is given as the same for each and every flip flop. Means all the flip flops are going to trigger at the same instant. They are going to trigger at the same instant. So this is called the synchronous series carry up counter. So series carry up counter means it is carry up means it is going to read from 0, 1, 2, 3 like that. So we are going to discuss the 4 bit. So this is circuit diagram. It is going to basically do the function of reading from up counter 0, 0, 0, 0, 0, 0, 0, 1 like that. So therefore it is going to read from 0, 1, 2, 3 like that up to 15 it is going to read, because it's a 4 bit. So it is going to read up to 15. So now this is initial stage is called as the LSB, and this is called as the MSB. Same thing in the case of the ripple counter also. The first one is called as the LSB, and the fourth one is called as the MSB. So the circuit diagram for the synchronous series carry up counter. Synchronous means all the flip flops are triggered at the same instant. So because of this it is called synchronous, and it is a series. You can see all this are in a series fashion. Carry up counter means reading from 0, 0, 0, 0 to like 0, 1, 2, 3 like that is going to read. So it is called up counter. So with the help of 4 bit we are going to choose. The number of bits is nothing but number of flip flops that we require. So this is the LSB means T0. Always you have to keep in the terminal condition, or you can say race around condition. So it is 1 here. So now this Q0. So Q0 now see this T1 is nothing but T1 is equal to Q0, and T2 is equal to, which is T1 into Q1, and similarly T3 is equal to Q2 into this into, which is a T2. So we are going to do like this. This is a T2 we are going to give. So this is the thing that we are going to give this one. So with the help of this circuit, so whatever the diagram we are going to give, it is basically up counter. So you can see clearly that T clock should be always given as equal to the propagation delay of the flip flop plus the setup time of the setup time plus the 2 times the propagation delay of the AND gate. You can see clearly these are the 2 AND gates. So 2 into propagation delay of the each AND gate. This is for the 4 bit. This is for the 4 bit. So the T clock should be always given as equal to the propagation delay of the flip flop, because all the flip flops are at one time they are triggering. So the flip flop the propagation delay is same. So therefore the propagation delay of each flip. If there are any flip flops, then it is always only one quantity, which is propagation delay of the flip flop plus the setup time plus the 2 times the propagation delay of the AND gate for 4 bits. Suppose if you go for the N bit, then the T clock should be always greater or equal to the propagation delay of the flip-flop plus setup time plus n minus 2 into propagation delay of the AND gate. So this is for the n bit. So for the ripple counter, I already told you the T clock should be always greater or equal to n times the propagation delay of the each flip-flop. Whereas here the T clock should be always greater or equal to the propagation delay of the flip-flop plus setup time plus 2 times the propagation delay of the AND gate, because there are two AND gates are there, so we have to go for the 2 times the propagation delay of the AND gate. This is for the 4 bit. Suppose if you go for the n bit, it is the clock time is always greater or equal to propagation delay of the flip-flop plus setup time plus n minus 2 into propagation delay of the each flip-flop, the propagation delay of the each AND gate. So we can see clearly, because in the ripple counter, the T clock should be always greater or equal to n times the propagation delay of the flip-flop, whereas this is the expression for the synchronous series carrier counter for 4 bit. So now we discuss another circuit. This is called as the synchronous parallel carry up counter for 4 bit. So as you can see clearly here, synchronous means all the flip-flops are the same clock, so all are going to trigger at the same instant. So this is called the synchronous. Whereas the parallel means here you can see clearly we are giving input in a parallel fashion. So we are giving input in a parallel fashion, and this is also a carry up counter for 4 bit. It is also doing the carry up operation, means 0, 1, 2, 3 like that. So this is called the carry up counter for 4 bit. So this is the circuit that we are going to get. So listen carefully here. This is called as LSB and this is called as LSB, and this is 1, and T1 is equal to 1 and T1 is equal to Q0, T2 is equal to Q1 into Q0 and T3 is equal to Q0 into Q1 into Q2. So with the help of this circuit we are going to get we can say carry up counter. So for n bit, what is the T clock should be always very equal to the propagation delay of the flip-flop plus setup time plus the propagation delay of the AND gate. This because all are in parallel, so only one we need. So therefore it is for n bit also. So therefore for parallel this is the T clock. So T clock should be always very equal to the propagation delay of the flip-flop plus setup time plus and the propagation delay of the AND gate, because all these are in parallel. So because of this only we need only one TPD irrespective of the number of AND gates, or irrespective of number of bits. So irrespective of number of bits, this is the time is constant. Whereas in the previous case, algorithms they are created in a series fashion, so therefore we have to use the n-2 there. In case of TPD, in front of that we have to use the n-2, but here there is no need. So now let me tell you how it is going to function. Let me tell you in a detailed manner. So here this is called as the present state, and this is called as the excitation state, and this is called as the next state. As I already told you, it is basically functioning. It must function like a carry up counter. So carry up counter means, I already told you, we have to go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is the present state is 0, the next state is 1. Again take 1 here, the next state is 2. Again 2 here, the next state is 3. Again 3 here, again next state is 4. Again 4 here, next state is 5. Again 5 again. So like this you have to continue like this. So the present state is 0, the next state must be 1, and here 1 means again 2. So 2 means here 3. So 3 means here 4. 4 means here 5. So 5 means 6. 5 means here 6. 6 means 7. 7 means 8. 8 means 9. 9 means 10. 10 means 11. 11 means 12. 12 means 13. 13 means 14. 14 means 15. So after the 15, you have to go back to the original 0. So like this you have to do this one. So this is the present state and this is the next state. So LSB is Q0, LSB is Q3. So Q3, Q2, Q1, 0. And also Q3 dash, Q3 plus, Q2 plus, Q1 plus and Q0 plus means next state. This is the present state. So then what is the excitation? Excitation inputs are nothing but T0, T1, T2, T3. So now if you want Q3 from 0 to 0, then what should be T3? It should be memory. So therefore T3 should be equal to 0. Similarly, if Q3 must change, if Q3 is changing from 0 to 0, then what should be T3? Again memory 0. So like that. So therefore for each and every input, we have to see what is output is changing. So from here to here, what you must change and what input that is required, we have to do the excitation for each and every thing. We have to take all these tables. So I will teach for only one thing and remaining thing that you have to understand. See here, for here, this was Q0 and Q dash naught, I will tell you. See, 0 to 0, 0 to 1 means I have to give which one? Traveling move, so it is equal to 1. So 1 to 0 means I have to give traveling 1. 0 to 1 means again I have to give traveling 1. So 1 to 0 means again I have to give traveling 1. So 0 to 1 means again traveling 1. Again 1 to 0 means again traveling 1. So 0 to 1 means again traveling 1. So change. 0 to 1 means again traveling 1. So like that we have to do this one. So we have to check from, see, 0 to 0 means you have to give memory of 0. Suppose 0 to 1 means you have to give traveling 1. 1 to 0 means again you have to give traveling of 1. 1 to 1 means you have to give a memory of 0. So based on this we have to fill the excitation tables for T3, T2, T1, T1. T3 means we have to check from Q3 to Q3 plus. What input that we have to give, so therefore we change from Q3 to Q3 plus. Similarly, what input that we have to give for T2, so therefore I have to be changing from Q2 to Q2 plus. Similarly, what input that we have to give for T1, so therefore I have to be changing from Q1 to Q1 plus. Similarly, what input that we have to give to T0, so therefore I have to change from Q0 to Q0 plus. So based on that, we have to draw this excitation table. So now, we know the inputs, we know the outputs. So try to figure out the T3 in terms of these expressions. Try to figure out the expression of T2 in terms of these expressions. Try to figure out the T1 in terms of these expressions. And try to find the expression of T0 in terms of these inputs. So now, we are going to get this expression. You can say T0 is equal to always 1 and T1 is always equal to Q0. You can say clearly T1 is always equal to Q0. Same thing we are going to get. Same thing. So T1 is always equal to Q0. And the T2 is nothing but it is a product of Q0 Q1. So Q0 and Q1. If it is a product of these two things, we are going to get T2. And the T3 is nothing but it is basically the product of Q0 Q1 Q2. So we are going to get product of Q0 Q1 Q2. All these things we are going to get with the help of K0. With the help of K0 we are going to get this expression which is T0 is equal to 1 and T1 is equal to Q0, T2 is equal to Q0 Q1 and the T3 is equal to Q0 Q1 Q2. So these expressions that we are going to get. So T0 is equal to 1, T1 is equal to Q0, T2 is equal to Q1 Q0, T3 is equal to Q2 Q1 Q0, T3 is equal to Q2 Q1 Q0. These expressions that we are going to get. So same thing we have done. So based on these expressions, we have to draw T0 is equal to 1, T1 is equal to Q0, T2 is equal to Q1 Q0, T3 is equal to Q2 Q1 Q0. So if you do like this, then we are going to get a, we can say, synchronous parallel carry-up counter for 4 bit because we are reading from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, again 0, 1, 2 like that. So this is the way we are going to design this circuit diagram. So this is our, based on this present state, what is the next state that you want and what is the execution which is required to make this from here to here. So like that if you do this one, then we are going to get this circuit. So based on this we have to draw this circuit. So this is the way that we are going to build a synchronous parallel carry-up counter for 4 bit. So now the next concept which is synchronous parallel carry down counter for 4 bit. So down counter for 4 bit. And what I told you down counter means here 0 to, see, if you go for 0 to 15, 15 to 14, 14 to 13 like that. We have to take all these tables same like this. So therefore present state, execution state and the next state. So 0 to 15, 15 to 14, 14 to 13, 13 to 12, 12 to 1, so 12 to 11, 11 to 10, 10 to 9, 9 to 8 like that we have to do this one. So if you take all this present state and next state and then try to find what is the execution required to change the output from here to from present state to next state. So based on that you are going to get some expressions for T3, T2, T1 and T0. When you draw the circuit you are going to get like this which is, so these are synchronous, this is LSB and this is the MSB. So for each and every flip-flop we are going to give the clock at the same time. All these are power stage triggering. So all are going to get triggered at the same instant. And we are going to get T1 is equal to 1 and T1 is equal to Q1 bar we are going to get and T2 is equal to Q1 bar Q0 bar and T3 is equal to Q2 bar Q1 bar Q0 bar. So this is the expression that we are going to get. So if you keep the circuit like this, then whatever the thing, the circuit is going to act like a down counter. So this is called synchronous parallel carry down counter for 4 bit. So this is the thing concept that you always have to keep in your mind. So present state, next state, and middle one is called as the excitation state. So what is excitation required to change the output from present state to next state? So based on this present state and the excitation, we have to find what is the excitation required. Then we are going to get some kind of expressions and try to bring the circuit. We are going to get this one. Sound it. Sound of it. So now we are going to learn about the ring counter using the D flip-flop. So we are building the ring counter using the D flip-flop. In detailed manner we are going to study now. As I already told you regarding the circuit of the ring counter using the D flip-flop, I have already told you, but I never told you in detailed manner. So now I will teach you in a detailed manner. So listen carefully. So I am going to take the 4 flip-flops. So this is D3, Q3, D2, Q2, D1, Q1, D0, Q0. This is Q3 bar, Q2 bar, Q1 bar and Q0 bar. I am going to give positive triggering for each and every clock, for each and every flip-flop. This is a synchronous because it is going to activate at the same time. So now I am going to take this like this. This output is given as input to here, this output is given input to here, this output is given input to here. So this output I have taken from Q1, I have taken a feedback and I given to D3. So this is called as the ring counter using the D flip-flop. So therefore each have the same frequency as the number of the clock is the frequency of F. So all these outputs have the same frequency, which is supply frequency by number of flip-flops, which is equal to 4. So we are going to get F by 4. So now suppose let me draw the we can see that in the graphical manner. So this is the clock that we are going to give. So all these are the positive triggering. So positive triggering. All these are positive triggering. So therefore initially I am going to assume everyone is having a 0 0 0 0, all having the same thing 0 0 0. So now this 0 is going to come here. So therefore this is a 0, right? So initially I am going to give certain data as input. See, I am going to open this feedback and I am going to give an input as 1. Initially I am going to open this feedback and I am going to give as input as 1. Then what is going to happen when the clock is scaled? It is going to become 1. Then see, if it is going to become 1 means here, this one is going to pass through here. Again it will pass through here. Again it will pass through here. Again it will pass through here. So like this we are going to get here. So you can see clearly whenever the clock is given, so this has passed up to here. So now this output is came up to here. So this output has came up to here. So this output has came up to here. So like this. Again you can see clearly this is the diagram. This is our diagram that we are going to get. So this is the diagram that we are going to get for this Q3, Q2, Q1 and Q0. This one is going to travel from Q3, then it goes to Q2, then it goes to Q1 and then it is going to Q0. Like this it is going to go. So you can see clearly, see I opened the feedback and I given the input as 1. So whenever the clock input is given, so this V1 is going to the Q3 and then it goes to the Q2 and then it goes to the Q1 and then it is going to the Q0 and then it is going to repeat. Again we are going to get the same repetition. Again here 1, again here 1, again here 1, again here 1. So this is the repetition that we are going to get. So I have drawn in this pictorial format. So now I will draw in the tabular format. So this tabular format is somewhat easier to analyze when compared to pictorial format. So listen carefully. Suppose initially I have not given any clock. So all these are going to have the same value of 0 0 0 0. See now I open the feedback and the given input is equal to 1 and now keep feedback again. See initially I open this feedback and the given input as 1. and then I close the feedback. Then what is going to happen? If I give input, when I give input as clock 1, it is going to have 1. Then this 0 comes here, this 0 comes here, this 0 comes here. Again next clock. So for the next clock, this 0 will comes to here. So this one comes to here, this one 0 comes to here, this 0 comes to here. So for the next clock, this 0 comes to here. So this 0 comes to here, this one comes to here, this 0 comes to here. So for the next clock, this 0 comes to here, this 0 comes to here, this 0 comes to here, this one comes to this position. And in the next clock, this one comes to here, this 0 comes to here, this 0 comes to here, this 0 comes to here. So same position, same thing we got originally, same thing we are going to get. Again we are going to repeat this process. So again we are going to repeat this process. So listen carefully. When I open the feedback and I give it 1 and then I close the feedback, then initially for the first clock we are going to get 1 0 0 0. And now here what I am going to do, I am going to do another clock. So this one goes to this side, this 0 goes to this side, this 0 goes to this side, and this 0 comes here. Similarly, if I give another feedback, so this 0 comes here, this 0 goes here, this one goes here, and this 0 goes here. For the next feedback, this 0 goes here, this 0 goes here, this 0 goes here, and this one goes here. For the next clock, this one goes here, this 0 goes here, this 0 goes here, this 0 goes here. So therefore, the same thing that we got initially, same thing is going to get repeated, and the output is going to get repeated in this fashion. So this is called as the ring counter using the D flip-flop. So we are going to get a certain sequence. So now we are going to analyze this one. You can see clearly only 4 states are repeating in 4-bit ring counter. You can see 1, 2, 3 and 4. Only these 4 states are repeating. See 1, 2, 3, 4. This is the same as the previous one. So for 4 bits, so 4 states are repeating for 4-bit ring counter. So we can say that only 4 states are repeating in the 4-bit ring counter. So this is a very important point. Only 4 states are repeating in the 4-bit ring counter. So therefore, generally we can say like this. So only 4 states are repeating in the 4-bit ring counter. So therefore, only n states are repeating in a n-bit ring counter. So for 4-bit ring counter, we are going to get 4 states. For general case, for n-bit ring counter, we are going to get only n states we are going to get. So in the n-bit ring counter, so the number of used states are n, and the number of unused states are basically 2 to the power of n minus n. And the output frequency at any flip-flop is supply frequency by number of used states. And the phase shift between the two successive waveforms is nothing but 360 by n. See, the phase difference between the two successive waveforms is nothing but 360 by n. So 360 by n is nothing but n is equal to 4. So 360 by 4 is nothing but 90 degree. So 90 degree is the phase shift between the two successive waveforms. Ring counter is fastest among all and ripple counter is the slowest among all. So ring counter is the fastest among all and ripple counter is the slowest among all. Ripple counter is fastest means we are going to get back the original again very faster. So only 4 states, only n states are used. So we are going to get double very faster when compared to other counters. So ring counter is the fastest among all and the ripple counter is the slowest among all. So these are the points that you always have to keep in your mind. So only 4 states are repeating for the in case of 4-bit ring counter and only n states are repeating in the n-bit ring counter. So in the n-bit ring counter the number of used states are n. So total number of unused states are 2 to the power of n minus n because the total number of states are 2 to the power of n. So minus used states are n. So if it is subtraction we are going to get number of unused states. And the output frequency of each and the output frequency of at any flip-flop is nothing but supply frequency by number of used states which is n. And the phase shift between the two successive waveforms is equal to 360 degree by number of used states n. And the ring counter is the fastest among all and the ripple counter is the slowest among all. So these are the very important points that you always have to keep in your mind. So only 4 states are repeating in a 4-bit ring counter. So only n states are repeating in n-bit ring counter. So in n-bit ring counter, the number of new states are n and the number of unused states are to the power of n minus n, because to the power of n is the total number of states and n is the used states. So subtraction we are going to get number of unused states, and the input frequency at any flip flop is equal to supply frequency by the clock frequency by number of used states. And the phase shift between the two successive waveforms is 360 degree by n. And the ring counter is the fastest among all, and the ripple counter is the slowest among all. So these are the important points that you always have to understand. See, I want you to told you, if you analyze this table, same thing we are going to get here also. Same thing we are going to get. If you analyze this one also, same thing we are going to get. See, initially what we have got, initially I want you to tell you, this is 0, 0, 0, 0, then we got 1, 0, 0, 0, then we got 0, 1, 0, 0, then we got 0, 0, 1, 0, then we got 0, 0, 0, 1. Same thing that we have got, same thing we have already told you, then we are going to get this back, same thing. So listen carefully, 0, 0, 0, 0, then 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, then we are going back to this position. So only 4 states, 1, 2, 3, 4, only 4 states are used. So this is a pictorial diagram and this is a tabular format, anything both are same. So this is the point that you always have to keep in your mind. So finally I can say, for a n-bit ring counter, the number of used states are n and the number of unused states are to the power of n minus n, and the output frequency of any flip flop is nothing but the supply frequency by number of used states, which is f by n, and the phase shift between the two successive waveforms is 360 by n, and the ring count is the fastest among all, and the ripple count is the slowest among all. We are going to study about the ring counter using the JK flip flop. In the previous case, we have learned about the ring counter using the D flip flops, but now we are going to study about the ring counter using the JK flip flops. So therefore you can see clearly this is the JK flip flop. So we are going to use the 4 bits. These 4 flip flops. The number of bits is equal to number of flip flops. So this is the we can say J3 K3, J2 K2, J1 K1, J0 K0. This is Q3 Q3 bar, Q2 Q2 bar, Q1 Q1 bar, Q1 Q1 bar. And what I told you, we have to do the clock for each and every one simultaneously. Means it is a synchronous clock. Means all are going to output at the same time. And if you see clearly, this Q0 is given to J3 and this Q0 bar is given to K3. So this is the way that we have to do the connection for the ring counter. So Q0 we have to give to J3 and Q bar we have to give to K. So this is the connection, and Q2 to J2 and Q3 bar to K2. Similarly Q2 to J1 and Q2 bar to K1 and Q1 to J0 and Q1 bar to K0. So this is a circuit connection that we have to give for the JK flip flop in order to act like a ring counter. So listen carefully. See, initially I am going to assume that all the states Q3, Q2, Q1, Q0 all are in a 0. All are in a 0. So now what I am going to do, I am going to open the feedback and E input is equal to 1 and now keep feedback again. So I am going to open this feedback and initially I am going to give this J3 is equal to 1 and after that I am going to close the feedback. So if I give the clock, then this is nothing but this 1 is going to travel to here. So this is 1. So this is 0 travels here. This 0 travels here. This 0 travels here. Similarly, if I give next clock, this 0 travels to here. This one travels to here. This 0 travels here. This 0 travels to here. Similarly, for the next clock, this 0 travels to here. This 0 travels to here. This one travels to here. This 0 travels to here. This creates a right shift. Again, for next clock, this 0 travels to here. This 0 travels to here. This 0 travels to here. This one travels to here. So for the next clock, we are going to get this signal. So this one, same thing is going to repeat. So we can say same thing. For a 4-bit, we are going to get 4 states. First state, second state, third state, and fourth state. So 4 unique states are going to get for the 4 flip-flops. For n flip-flops, we are going to get n number of used states. Same thing I wanted to tell you. So this is the circuit connection for the ring combination the JK flip-flops. So if starting state is 0, 0, 0, 0, then both the previous circuits always stays in that state for all time. Yes. If all are having the same state 0, 0, 0, 0, if you are not opening the feedback and if you are not doing 1, then definitely all the states are going to stay in the 0, 0, 0, 0 for around their lifetime. So therefore we have to, for the two circuits, For the we have made the ring counter using the D flip flop, and also we have made the ring counter using the JK flip flop. So in these two flip flops, always you have to open the feedback and you have to give initial event, and then you have to close the feedback. Then only it is going to act like a ring counter. Suppose if you are not opening the feedback and if you are not giving any input 1, then it is always going to stay in the 0 0 0 0 for all its lifetime. So therefore, if starting state is 0 0 0 0, then both the previous circuits always stays in the state for all the time if you are not opening that feedback and if you are not giving the 1. So this is a point that you always have to keep in your mind. So now I will build a new circuit. So now I am going to build a new circuit which is called as a self-starting ring counter. So this is the other type of ring counter. It is a self-starting. Means you don't have to open the feedback and you don't have to give the 1 always. So therefore this is called a self-starting ring counter. So we can see clearly this is basically right shifting. So right shifting is data shift from Q3 to Q2, Q2 to Q1 and Q1 to Q0. So now here this Q3, Q2, Q1 I am going to do the X. We can say this is called as the NOR gate. So this is called the NOR gate. So I am going to do the NOR operation of Q3, Q2, Q1 and I am going to give this as an input to the Q3, and then I will see what is the nature that we are going to get. So initially clock is equal to 0 means I am going to assume all the states are 0, 0, 0, 0, 0. Suppose if the clock is equal to 1, then what is going to happen? I already told you these 3 are 0, 0, 0. So OR gate is nothing, NOR gate is nothing but 0 plus 0 plus 0 all 1 is equal to 1. So 1 we are going to get. So this 0 travels to here, this 0 travels to here, this 0 travels to, this 0 travels to here. Again keep this NOR. So again NOR is how much? Again NOR is nothing but, again you are going to get 0. So you are going to get 0 as input here. This 1 travels to here, this 0 travels to here, this 0 travels to here. Again this is something but again the NOR operation of these 3 things we are going to get 0. So 0 we are going to get here. So 0 travels to here, 1 travels to here and 0 travels to here. Again the NOR operation of this we are going to get again 0. So you are going to get 0 as input here. This 0 travels to here, this 0 travels to here and this one travels to here. Again all these zeros, again NOR operation is nothing but simply we are going to get 1. So then we are going to get 1 here and see then we are going to get 1 here. So this 1 we are going to get here. Again 0 we are going to get, 0 we are going to get, 0 we are going to get. Means this is the state that we are going to get. So we can say again it is going to repeat. So how many number of unique states? 1, 2, 3, 4. Only 4 states are unique states. That is the self-starting. So for 4 flip flops we are going to get 4 unique states. For n flip flop we are going to get n unique states for the ring counter. But it is self-starting. We don't have to open the feedback and we don't have to give the input as 1. Because it is automatically it is going to get start because of this NOR operation. So we can see only 4 unique states are going to present. 1, 2, 3, 4. Only these 3 things are going to present. These are the unique states. It is a starting state. It is not available in the unique states. So only these 4 states are going to present. So that's called as the self-starting ring counter because you know that you don't have to open the feedback and you don't have to give the input as 1. So it is going to repeat all this time. All time it is going to repeat in this loop. So always only 4 unique states are going to present. So now we are going to study about another concept is called as the Johnson ring counter. Johnson ring counter I already told you. I already told you the basic diagram but I never told you in detail. But now it's time to learn about this one in a very detailed manner. So you can see I am going to consider the 4 flip flops. 4 flip flops. So with the help of D flip flop, with the help of D flip flops I am going to make this Johnson ring counter. So this is a circuit diagram if you want to make the Johnson's ring counter with the help of D flip flops. So D3 Q3, D4 Q2, D1 Q1, D dot Q dot. So here this Q3 is given input to D2, Q2 given input to D1, Q1 given input to D0 and Q0, see this is a Q0. But you have to take feedback from Q0 bar. So Q0 bar you have to take feedback and you have to go to here. If you take feedback from here means it is a ring counter, but if you take from here means it is called as the Johnson's ring counter. So if you take feedback from Q0 bar means it is called as the Johnson's ring counter. See all these flip flops are going to trigger at the same instant with the help of clock. So it is called as synchronous. I have already told you one important point here. This is called as the Johnson's ring counter. Johnson's ring counter. And here the frequency at each and every output is nothing like this. Here supply frequency by number of used states. Here number of used states are 2 into number of flip flops. So number of flip-flops are 4. So 2 into 4 is nothing but 8. So total 8 states are used. So F by total number of used states in the Johnson's encounter is 2n. This 2 into 4 is nothing but 8. So F by 8 is the frequency and each and every output we are going to get here. So this is a circuit diagram if you want to make the Johnson's encounter with the help of the flip-flop. So this is a circuit diagram if you want to make the Johnson's encounter with the help of JK flip-flop. So JK flip-flop means I have already told you this is the J3 K3, J2 K2, J1 K1, J0 K0. This is Q3 Q2, Q3 bar, Q2 Q2 bar, Q1 Q1 bar, Q1 Q1, Q0 bar. So this Q3 has given input to J2, this Q3 bar given input to K2, this Q2 is given input to J1, this Q2 bar is given input to K1, this Q1 is given input to J0, this Q1 bar given input to K0. But here we have to take reverse fashion. From Q0 we have to give feedback to K3 and from Q0 bar we have to give feedback to J3. Suppose if you take from Q0 bar to K3 and Q0 to J3 is nothing but it is called the ring counter. But if you take in a reverse fashion it is called the Johnson's ring counter. So from Q0 if you take to K3 and from Q0 bar if you take to J3 it is called as the Johnson's ring counter. So this is called the supply frequency of the clock frequency is called F. And only told you at each and every output the frequency is equal to supply frequency by number of used states in Johnson's ring counter is 2 into n. As I use number of flip-flops are 4, so 4 to say 8, so we are going to get a frequency by 8. So F by 8 is the frequency at each and every output of the Johnson's ring counter we are going to get. So this basically I have already told you these two are not self-starting, so initially we have to open the feedback and we have to give the input as 1. Whereas here this is basically, you can see clearly, this is called a self-starting Johnson's ring counter. So here we are taking a NOT gate, here we are taking a NOT gate here and we are taking from here. So this is called as the, we can say a simple diagram which is representing the Johnson's ring counter. So this is simple diagram which is telling you about the Johnson's ring counter. So now these are three circuits, but the table is same. So now we are going to analyze. See carefully here. So listen carefully. Initially I am going to assume all the states are 0, 0, 0, 0. But one important point is here, you don't have to open the feedback. I told wrong. Here you don't have to open the feedback because if Q is equal to 0 means Q bar is equal to 1. So by default you are going to get here 1 here. So if this is 1 means you are going to get 0 here, 0 here and 0 here. Again here 0 means Q bar is equal to 1. Again 1 you are going to get here. So again 1. So this 1 goes to this side, this 0 goes to this side, this 0 goes to this side. If Q is equal to 0 means Q bar is equal to 1. Again 1 comes here. So this 1 travels to here, this 1 travels to here, this 0 travels to here. Again this is 0. Again 0 bar is nothing but 1. But 1 comes here. So this is 1 comes here, this 1 comes here and this 1 comes here. This is Q is equal to 1. So Q bar is equal to 0. That goes to this side. So this is 1 here and this 1 here and this 1 here. Similarly, if this is 1, again that Q bar is equal to 0. That 0 comes here. And this 0 travels here, this one travels here, and this one travels here. If this is 1 means Q bar is equal to 0, the 0 comes here, so this 0 goes here, this 0 goes here, and this one goes here. Similarly, this is 1 means Q bar is equal to 0, that comes here, so this 0 travels here, this 0 travels here, this 0 travels here. So indeed we are going to get the first case, and then we are going to repeat this process. So this is the loop. If you count the number of states used are 1, 2, 3, 4, 5, 6, 7, 8. Only 8 states are used. You can see clearly only 8 states are used. For this 4-bit flip-flop, we are going to use the 8 states. So this is the point that you always have to keep in your mind. So we can see analysis packages. This is also called as the walking counter or creeping counter or Mobius counter or twisted ring counter. So Johnson's ring counter is also called as the walking counter or creeping counter or Mobius counter or twisted ring counter. These are the different names for this Johnson's ring counter. It is also called as the walking counter or creeping counter or Mobius counter or the twisted ring counter. So in n-bit Johnson's ring counter, the number of used states are 2n because for 4-bit the number of used states are 8. So therefore generally for n-bit the number of used states are 2n. Then the number of unused states are basically putting is to the power of n minus used states are 2n. So therefore with this approximation we are going to get number of unused states is to the power of n minus 2n. And the frequency at any flip-flop output is nothing but which is f1 is equal to clock frequency by number of used states is 2n. So this is the point that you always have to keep in your mind. So we can see that the frequency at any output flip-flop is nothing but clock frequency by number of new states is 2n. So this is the point that you always have to keep in your mind. So therefore, this Johnson's ring count is also called as the working counter or creating counter or Morris counter or twisted ring counter. And for any bit Johnson's ring counter, the number of new states are 2n and the number of unused states are 2 to the power of n minus 2n. And the frequency at any output of any flip-flop is clock frequency by number of new states, which is 2n. So n by 2n is the frequency at any output of the flip-flop. So these are the points that we always have to keep in your mind. See, we don't have to open the feedback and we don't have to give the 1 because by default we are going to get the 1 as the input because of not bar. So this is the point that you always have to keep in your mind. So now we are going to discuss another new concept is called as the, see a small question here, designing, we are designing a synchronous counter using a D flip-flop for count. So here basically, so we are designing a synchronous counter using the D flip-flop for count. So this is a count that we always need 0 0 1 0 0 1 1 1 and then we want the again thing which is like this 0 0 means 0 1 0 means we can say 2 and 0 1 means 1 and 1 1 means basically it is a 3. So we can say randomly. So random I want this sequence. So this sequence I want the sequence to be designed like this with the help of synchronous counter. So listen carefully. In the ripple counter, always you can get only sequence, which you can do only through a sequence. You cannot get a sequence which is not in a sequence manner. You cannot design the sequence which is, and we see with the help of ripple counter, you can only design a counter which is in a sequence manner, like 0, 1, 2, 3, 4, or simply 7, 6, 5, 4 like that. You can only build in the sequence. But if you want a sequence which is not in a proper sequence, like randomly, like 0, 6, 3, 2, 1, then you can't build with the help of ripple counter. But you can only build with only synchronous counters. Synchronous counter means I already told you for all the flip-flops simultaneously if you are going to give the clock, it is called as a synchronous counter. So that is the meaning of synchronous. So we are going to design a synchronous counter using the D flip-flop for this count, which is the random count, which is 0 0 1 0 0 1 1 1. So I already told you, if you want to design, first you have to know what is the previous state and then the next state. So basically we have only 2 steps. We can say only 2 digits are there, it's 2 binary bits. So we have to build 2 flip-flops. The number of which is equal to number of flip-flops we are going to design. So therefore here is the Q1 Q0, this is the Q1 Q0. This is called the previous state and this is called as the next state. So what is the initial state 0 0, then we want next 1 0. So we keep 1 0, again next state we need 0 1 and then we keep 0 1, then we want the 1 1 and if you want your 1 1, the next state is 0 0. So same thing it is going to repeat. So this is the previous state and this is the next state. So 0 0 means next state is 1 0, here 1 0 means next state is 0 1, here 0 1 means next state is 1 1, here 1 1 means next state is 0 0. So again you are going to repeat this process. So this is the sequence that we always want. So this is the previous state and this is the next state. Then what is the excitation inputs that require in order to change the previous state to next state? So what are the excitation inputs? This is the D1 and this is the D0 because the D flip-flop means D1, D0. So if you want 0 to 1 means we have to do D1 as 1. For 1 to 0 we have to do D1 as 0. For 0 to 1 we have to do D1 as 1. For 1 to 0 we have to do D1 as 0. Similarly for 0 to 0 we have to do D0 as 0. For 0 to 1 we have to do D0 as 1. For 1 to 0, for 1 to 1 we have to do D0 as 1. For 1 to 0 we have to do D0 as 0. So this is the excitation case are required to change the previous state to next state. Then with the help of this, so these are called as the, so now write the key map for this D1 and D0 in terms of Q1, Q0. So simply we can say D1 is nothing but Q1 bar, Q0 bar plus Q1 bar, Q0. So Q1 bar plus Q1 bar, Q0. If you simplify this one, simply we are going to get Q1 bar. So if you take Q1 bar as a common, just Q1 bar plus Q0 is equal to 1. So 1 into Q1 bar is equal to Q1 bar. So Q1 bar we are going to get for D1. Similarly, I want to simplify D0 in terms of these things. Then what is D0? So D0 is nothing but we are going to get Q1 into Q0 bar plus and Q1 bar into Q0. So this is I am writing in terms of SOP form. So if you simplify this one, we are going to get basically it is called as the Q1 XOR of Q0. So it is basically Q1 XOR of Q0. So now we know the input values D1 and D0. So now we have to build this circuit. So this is called as the D1 flip-flop and this is called the D1 flip-flop. So this is called as the MSB and this is called as the LSB because D1 is the MSB and D1 is LSB. So now I wanted to use synchronous means clock is same for both the things. So see, the clock is going to execute both the flip-flops at the same instant. So because of this it is called synchronous counting and we are going to go for the positive edge triggering. So therefore now this is the D1 Q1 Qn bar. This is D0 Q0 Q0 bar. See what is the value of D1? D1 is nothing but Q1 bar. So Q1 bar is nothing but this is the from here you have to take this one and you have to give here. So D1 is equal to Q1 bar. Similarly, what is D0? D0 is equal to Q1 XOR of Q0. This is the Q1 and this is Q0. You take these two outputs, then you have to take these two windings and you have to give the XOR gate and then this is given to D0. So this is a circuit, it is going to function. So now this can get the values of the sequence that you really want. So now we can get the 0, 0, 1, 0, 0, 1, 1, 1 and 0, 0. This sequence we are going to get with the help of this circuit diagram. So this circuit is going to give you the results of the design which we want 0, 0, 1, 0, 0, 1 and 1, 1. So now we are going to learn about another new concept here. We are going to analyze the given circuit assuming the initial state around 0. So this is a circuit we are given. So now I am going to analyze the circuit. I am going to assume that all the initial states are 0. So basically this is a circuit they are given in this question and they are asking me to analyze this circuit. I am going to assume that all the initial states are 0. So now let me see, basically if you see clearly these two are negative triggering and also clock is given both for them continuously at the same time. Means this clock is going to give the activation for these two flip-flops simultaneously. So it is called synchronous. Basically it is called synchronous some flip-flops. So now we are going to write this table, present state and the next state. And this is called as the execution inputs. Inputs are basically J1, J1 K1 and J2 K2. If you see clearly one important point, J1 is nothing but it is equal to J1 is equal to basically Q2 bar and K1 is also equal to Q2 bar. Similarly, what is J2? J2 is equal to Q1 bar and K2 is equal to 1. So now I am going to assume the present state is, I am going to assume the initial states are 0 and 0. Q1 is equal to 0 and Q2 is equal to 0. Then what is this Q2 bar? Q2 bar is equal to 1, 0 bar is equal to 1, here also 0 bar is equal to 1. What is Q1 bar? 0 bar is equal to 1 and this is 1. Now if I give this excitation inputs, what is going to get changed? So whenever you give 1, 1 and if you give 1, 1 as input, so Q1 bar will be in the toggling mode. So it is going to change from 0 to 1. Similarly here also toggling mode. So it is going to change from 0 to 1. Now this state will come here. Now same thing. Again Q2 is 1. So Q2 bar is equal to 0. Q2 bar is equal to 0. Q1 bar is equal to 0 and K2 is equal to 1 here. It is always 1. So now if you see clearly for 0, 0. If you do 0, 0 means memory. So what is the previous state? Same is going to present. So it is 1 means here also 1. Suppose here 0, 1 means you are going to get again 0. So Q2 you are going to get 0. So you are going to get Q2 as 0. So same thing we are going to give here 1, 0 again. Then what is Q2 bar? 0 bar is equal to 1. Q2 bar is again 1. So Q1 bar is nothing but 0 and his K2 is equal to 1. So if you give 1, 1, we are going to get toggling mode. Because 1 means it will become 0. Here 0 1 means basically I wanted to get. So Q2 we are going to get 0. So 0 we are going to get. So same circuit is going to get repeat. So again we are going to get the same thing. Same repetition. So therefore we are going to get the states like this. 0, 0, 1, 1, 1, 0. Again repetition to 0, 0, 1, 1, 1, 0. Again 0, 0, 1, 1, 1, 0. So it is in the repetition process. So the output sequence is 0, 0, 1, 1, 1, 0. Again 0, 0, 1, 1, 1, 0. Again 0, 0. So this is the sequence that we are going to get from this circuit diagram. So now we are going to design the relay and Moore state machine to detect the 110 sequence. So this is a very important concept that you always need to understand. See, we are going to design the relay and also Moore state machines to detect the 110 sequence. Suppose we have a sequence like this, random sequence 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0. So I want to detect the sequence of 1, 1, 0 with the help of relay and also Moore. So with the help of Mealy state machine and Moore state machine, I want to design to detect the 110 sequence. Then what is the value of output y? 0 means 0, 0 means 0. See, whenever the sequence is 110, then it is going to give me 1. Otherwise, it is going to give me 0. So 0 means 0, 0 means 0, 1 is 0, 1 is 0. But now, if you see, we are going to get 0, 1, 1. Yes, a sequence is detected, so you are going to get 1 here. Again here 0 means 0, 0 means 0, 0 means 0. Again here 0, 1 is 0, 1 is 0. Here, if you see clearly, these 3, we are going to get 1, 1, 0. A sequence is detected, so we are going to get again 1. Again for 1, 0, for 0, 0, for 0, 0, for 1, 0, for 1, 0, for 0. If you see clearly, again 1, 1, 0 sequence, then we are going to get 1. So, for a particular input, you have to see the past 2 outputs. Past 2 inputs you have to combine, all the 3 inputs you have to combine, and if you see, if 110 is detected, then the corresponding output is 1, otherwise it is 0. So like this you have to do this one. So for 0 means 0, for 0 means 0, for here 0, 0, 1 means here 0, here 0, 1 means 0, but here 1 means 0 means 1, again 1, 0, 0 means 0, 0, 0, 0 means 0, 0, 0, 0 means 0, 0, 0, 1 means 0, 0, 1 means 0, 1, 1, 0 means 1, 1, 0, 1 means 0, 0, 1, 0 means 0, 0, 1, 0 means 0, 1, 0, 0 means 0, 0, 1 means 0, 0, 1, 1 means 0, 1, 1 means 1, 1, 0 means 1. So we have to see the 3 grouping. So 3 grouping we have to see, and we have to check whether if it is 1 and 0, then only we are going to get as 1. Otherwise we are going to get 0. So based on this is the random input and this is the output that we are going to get, because we want the sequence 1 and 0 to be 1. So now this is a Mealy state machine. So now listen carefully. Mealy state machine. It's a very important concept. So Mealy state machine. So here I am going to use state S0, and then state S1 and state S2. Listen carefully. Whenever the input is equal to 0, whatever the output should be always equal to 0, same state. Suppose if input is equal to 1, so if input is equal to 1 means, it has to go from state 0 to state 1 with an output of 0. Again, for this one, if suppose if the state is again 1, means again it has to go to the new state 1 with an output of 0. Suppose if the new state is, if the input is again 0, then we are going to get output as 1. We have to go back to the original state. Listen carefully. Suppose if this is state 0, state 1 and state 2. For the state 0, if the input is 0 means output should be equal to 0. Suppose if the input is 1 means the output should be equal to 0, and it has to move to state 1. Similarly for the state 1, if the input is 0 means the output should be equal to 0 and it has to go here. Otherwise, if input is equal to 1 means it has to go to the state with the output of 0. Similarly, at here, if the state is again 1 means it has to become again, if the input is 1 means output should be equal to 0, and if the input is 0 means the output should be 1 and it has to go to the state 0. So this is a circuit diagram, or we can say a Mealy state machine. So this we are going to get like this. So for the state S0, suppose if the input is 0 means output should be equal to 0 and it has to stay in the same S0 state only. Suppose if the input is 1 means output should be equal to 0 and it has to move to the state 1. Suppose if the input is 0 means output should be 0 and it has to go back to the initial state. Suppose from here, if the input is 1 means the output should be equal to 0 and it has to move to state 2. Here, suppose if the input is 1 means the output should be equal to 0 and it has to present in the same state 2. Suppose if the input is 0 means 110 sequence is detected, so output should be equal to 1 and it has to move to the state 0. Again we have to do the initial. From initial we have to do this one. So this is the Mealy state machine that we are going to get from this random input X. So from this we can get the 110 sequence. So therefore this is we can say a Mealy state machine we are going to get. This upper part is called as the input and the downput is called as the corresponding output. So So now Moore state machine. So for Moore state machines, there will be 4 states: S0, S1, S2 and S3. So listen carefully. Suppose if the input is 0, definitely output will be always equal to 0. Suppose if the input is 1, then we have to go to the new state with the output always equal to 0. Again, if the input is equal to 0 means it has to go to the initial state and it also always be 0 here. Similarly from here, if the input is again 1 means it has to go to new state with output of 0. Suppose if the input is 1 means always it has to stay in that state with the output of 0. Suppose if the input is 0, means output should be always equal to 1 because we have detected the 110 in this fashion or 110 in this fashion. So we are going to get output of 1. Suppose from here, suppose if the input is 1 again, means we have to go for this state with the output of 0. Suppose if the input is 0 means it has to go to this initial state with an output of 0. So this is called as the Moore state machine. So if you see clearly, initial input letters is going to come earlier than O. So this thing is Moore, then next is the Moore. Easy to remember. In the English alphabets, E is going to come earlier than O. So we can say Moore state machine is going to come earlier than the Moore state machine. If the number of states are 3, but here the number of states are 4. So this is a circuit that we can see a state machine diagram we are going to get in order to detect the sequence 1, 1, 0. So listen carefully. This is called as the input and this is called as the outputs. This part is going to give you the output and this is called as the input. So whenever you give an input as 0, output will be always equal to 0. If you state 0 is 0. If you give input as 1, we are going to do this new state of S1 with an output of always equal to 0. If again the input is equal to 0 means we are going back to the initial state with the output is always equal to 0. Similarly, if the new input is 1 means we are going to go for the new state S2 with the output of always equal to 0. If the new input is again 1 means the output is always equal to 0, we are always present in the same state S2. If the input is 0 means we are going to the new state with an output of 1. Similarly, if the input is 1 means we are going back to this state S1 with an output of 0. Suppose if the input is here 0 means we are going back to the initial state S0 with an output of 0. So this is the Moore state machine that we are going to get. So this is the Moore state machine diagram that we are going to get from this thing. So this is the Moore state machine and this is the Moore state machine in order to detect the sequence 1, 1, 0. So 1, 1, 0. So Moore is in the alphabetical orders, initial alphabetical orders is going to come earlier than O. So Moore state machine is going to come earlier than the Moore state machine. So now we are going to discuss about some important conclusion regarding the Moore state machine and the Moore state machine. So in a Moore state machine, for to detect the n-bit sequence, we require n states and always the n small n values always get equal to log n with a base 2. N is called as the number of flip-flops. So basically in a Moore state machine, I already told you, in a Moore state machine, if you want to detect the n-bit sequence, capital n-bit sequence, then we require n states. And also, I already told you to the power of small n. So suppose if there are n flip-flops means we are going to get to the power of n states we are going to get. So therefore simply we can say to the power of n states means always to the power of n is always greater than or equal to n. So if you take this one, we are going to get n greater than or equal to log n base 2. So basically in a Moore state machine, I want to tell you, if you want to detect a n-bit sequence, then definitely we require n states. So we are going to require n states. Suppose with n flip-flops, we can get to the power of n states. With the help of n flip-flops, we are going to get to the power of n states. So to the power of n is always greater than or equal to n. So if we take log base 2 on both sides, we are going to get n is greater than or equal to log n base 2. So this is called as the number of flip-flops we are going to require. N is called as the number of flip-flops. So this is the expression that we are going to get. So therefore, in a linear state machine, if you want to detect an input sequence, then definitely you are going to require n states. So you are going to require n states. And also, so therefore, to detect the input sequence, we are going to require the n states. And always, for n number of flip-flops, the number of combinations to the power of n is always greater than or equal to n. So it is always greater than or equal to n. So therefore, n is greater than or equal to log n base 2. When n is called as the number of states or number of bit sequence, and n is called as small n is called as the number of flip-flops. So you can say clearly, to detect the 3-bit sequence, we require 3 states in the relay state machine. So in order to detect the 3-bit sequence, we are going to require the 3 states in the relay state machine. Similarly, in the relay state machine, to detect the n-bit sequence, we require n plus 1 states, and n is always greater than or equal to log n plus 2 base 2, which is called as n is called as small n is called as the number of flip-flops. Same concept we have to apply. So we can say in a relay state machine, in order to detect the n-bit sequence, we require n plus 1 number of states. So if small n is the number of flip-flops, means to the power of n is the total number of states. So total number of states should be always greater than or equal to n plus 1. So if you simplify, we are going to get n is greater than or equal to log of n plus 1 base 2. So you can see clearly, if you want to detect the n-bit sequence, then we are going to require n plus 1 states. So therefore, I already told you, if there are n flip-flops, so to the power of n combinations, to the power of n states we are going to get. So to the power of n is always greater than or equal to total number of states is n plus 1. So if you take log base 2 on both sides, we are going to get n is greater than or equal to log of n plus 1 to the base 2. So these are the important points that you always have to keep remember. So therefore, finally I can say, in a linear state machine, in order to detect the n-bit sequence, we are going to require n states, and the number of flip-flops are n, small n. So total power of n is total number of states is always greater than or equal to n. So if you apply log base 2 on both sides, we are going to get small n greater than or equal to log n base 2, where n is called as the number of flip-flops and capital is called as the number of bit sequence or number of states. Similarly, in a linear state machine, in order to detect the capital bit sequence, we require n plus 1 states. And also, I already told you, if it is the number of small n is the number of flip-flops, then total states are to the power of n is always greater than or equal to total number of states is n plus 1. So if you take log base 2 on both sides, we are going to get n is greater than or equal to log of n plus 1 with the base 2. So these are the important points that you always have to remember. So you can see clearly from this picture also, in order to get the 3-bit sequence, we are going to require the 4 states in the relay state machine. So this is the concept. These 2 formulas that you always have to keep understanding, and you have to remember these 2 things. We are going to analyze the simplifying the below state diagram. So this is a state diagram they have given, a complex state diagram. So now we have to simplify this below state diagram, we have to simplify this one. So listen carefully, they are given state diagram in this fashion. It's a very complex state diagram. See, this is the state A, state B, state C, state D, state E, state F and state G. So whenever the input is 0 and output is 0, we are going to be in the same state. Similarly, whenever the input is equal to 1, so we are going to move to state B with an output of 0. Similarly, from here, state B, if you see clearly, if you give an input of 0, then we are going to get an output of 0 and we are going to move to state C. But if you give an input of 1, then we are going to go to this state B with an output of 0. From here, if you give an input of 1, so we are going to move to state F with an output of 1. Similarly, if you from here, if you give an input of 1, we are doing the same state F with an output of 1. Whereas if you give an input of 0, then we are going to move to state J with an output of 0. But if you give an input at 1 from state J, then we are going to move to state F with an output of 1. Similarly, if you give an input of 0 from state J, then we are going to move to state A with an output of 0. Similarly from here, if you see clearly from state B, state E, if we give an input of 0, then we are going to get output of 0 and we are going to move to state A. And if you give an input of 1, then we are going to move to state B with an output of 1. So this is what that we always have to see. So from state C, if you give an input of 0, then we are going to get output of 0 and we are going to move to state A. Similarly, if you give an input of 1 and then we are going to get output of 0 and we are going to move to state B. So this is the complex state diagram they have given. So now we are going to basically simplify this circuit. So you can see clearly here. You can see clearly from this diagram. See, suppose this is the previous state and this is the next state, and you can see the output state. So you can see clearly this is basically previous state and this is called next state and this is the output. Suppose if the state is A, you can see clearly if the state is A and the next state, suppose if you give x is equal to 0, if you give input is equal to 0, we are doing the same state A with an output of 0. So therefore, we are going to, when x is equal to 0, we are in the same state A and we are having an output of 0 when x is equal to 0. Similarly, suppose if we give input x is equal to 1, if you give x is equal to 1, we are moving to state B. So if x is equal to 1, we are going to move to state B with an output of 0. Similarly, for B, if you see clearly for B, suppose if you give an input x is equal to 0, then we are moving to state C with an output of 0. So we are going to move to state C with an output of 0. Suppose if we give input x is equal to 1, then we are moving to state B with an output of 0. So for x is equal to 1, we are going to move to state B with an output of 0. Similarly from C, you can see clearly for C, suppose if you give input x is equal to 0, then we are going to state A with an output of 0. So we are going to state A with an output of 0. Suppose if we give input is equal to 1, then we are going to state D with an output of 0. So if we give input x is equal to 1, we are going to move to state D with an output of 0. Similarly from D, you can see clearly, if you give input x is equal to 0, then we are moving to state E with an output of 0. So then we are going to move to state E with an output of 0. Suppose if we give input x is equal to 1, then we are going to move to state F with an output of 1. So we are going to move to state F with an output of 1. Similarly, from E you can see clearly, from E, if we give input x is equal to 0, then I am going to move to state A with an output of 0. So I am going to move to state A with an output of 0. Similarly, if I give input x is equal to 1, then I am going to move to state F with an output of 1. I am going to move to state F with an output of 1. Similarly from F, if I give input x is equal to 0, then I am going to basically state G with an output of 0. So I am going to state G with an output of 0. If I give input x is equal to 1, then I am going to be in the same state F with an output of 1. So I am in the same state F with an output of 1. But here, for G1, you can see clearly for the G, suppose if I give input x is equal to 0, then I am going to move to state A with an output of 0. So I am going to move to state A with an output of 0. If I give an input x is equal to 1, then I am going to move to state F with an output of 1. So I am going to state F with an output of 1. So this is the diagram we can see. This is what we are going to analyze from this complex state diagram. So this is called the previous state, and what is the next state and what is the output. So this is called as the next state and this is called as the output. Then for x is equal to 0, one state, for x is equal to 0, one output. For x is equal to 1, another state, and for x is equal to 1, what is the corresponding output. So we have drawn in this fashion. So this is called as the previous state and this is called as the next state. For input x is equal to 0, what is the next state and what is the output for that x is equal to 0. Similarly, for x is equal to 1, what is that state and what is the corresponding output we are going to draw in this table in this format. So all the information about this state diagram we have drawn in this simple table. So now if you see carefully, E is equal to G. So E is equal to G because E is equal to G because here it is A, here it is A, here it is F, here it is F, here it is 0, here it is 0, here it is 1, here it is 1. So we can say E is equal to G. So this total E is always equal to G. So everything is same. So basically we can say this E that is this one, A, F, 0, 0, 1, 1. So both are identical. So E is always equal to G. Similarly, D is equal to F. So if you take D and F, you can see here F, 0, 0, 1, 1. E is equal to G. Just now we have seen D is equal to G. So therefore, D is also equal to F. So from this we can say, so if you compare all these things, we are going to get these two rows are equal and these two rows are equal. So finally, E is equal to G and D is equal to F. These two things we are going to get. So remove last two rows. So see, this D is equal to F and A is equal to, and see, D is equal to, basically we can say, what I am trying to say is very simple. Here E is equal to G. So we can see this E is equal to G and D is equal to F. So D is equal to F and E is equal to G. So therefore, I am going to remove these two things. The last two rows I am going to remove. Only the remaining things I am going to consider because these two rows are same. So these two rows and these two rows are same. So I am going to neglect this F and G. So I am going to neglect this F and G and I am going to consider only up to A, B, C, D, E. Only these rows up to A only I am going to consider because these are identical. So I am going to remove them from this diagram, from this block. So therefore we are going to get, so I am going to remove the last two rows. So remove the last two rows. So remove the last two rows. Because D is equal to F and E is equal to G, so we are going to remove this last two rows. So now what is the table that we are going to get is a very simple table. You can see this is called the previous state, next state, and this is the output. So what is the next state for x is equal to 0, what is the next state, and for x is equal to 1, what is the next state, and for x is equal to 0, what is the output, and for x is equal to 1, what is the output. So you can see clearly, this is A, B, 0, 0. So A, B, 0, 0, same thing we have seen. BCD 0, 0. So BCD 0, 0. Next is CAD 0, 0. CAD 0, 0. Here DEF. DEF. F is equal to D. So in place of F and writing is DA. Again 0, 1, 0, 1. Here it is E. AF 0, 1. F is nothing but it is equal to D. So I written DL 0, 1. So whatever the values you have to write, those values should be present here. So only these letters you have to write, only those letters you have to write which are present in these states, not the things which is not there. See, F is not there. So because I am removing the F, so you don't have to write the F. Because I am removing the F row, so you don't have to write the F. So what is the F? F is equal to D. Similarly, I am removing the G. I am removing the G also. So like that you have to write here. So F and G I am removing. So in place of F, write D. So the things which are present in this only state only you have to use, only those variables you have to use here. So now this is the simple state diagram we are going to use. So now with the help of this diagram we are going to draw the simple state diagram we are going to draw. So here this is the state A. So listen carefully. Whenever the input is equal to 0, it is having the same state of output 0. So same state, whenever the input is equal to 0, it is having the same state with an output of 0. Similarly, if input is equal to 1 means it is going to state B with an output of 0. So whenever the input is equal to 1 means it is going to state B with an output of 0. Similarly, from state B, if input is equal to 0 means it is going to state C with an output of 0. So from B, if input is equal to 0 means it is going to state C with an output of 0. If input is equal to 1 means it is going to state D with an output of 0. So if input is equal to 1 means it is going to state D with an output of 0. Similarly from C, if input is equal to 0 means it is going to go to state A with a 0. So therefore, from C, if input is equal to 0 means it is going to state A with an output of 0. Similarly, if input is equal to 1 means it is going to state B with an output of 0. Similarly from D, you can see when input is equal to 0, it is going to state A with an output of 0. So therefore, whenever the input is equal to 0, it is going to go to state A with an output of 0, and whenever the input is equal to 1, it is going to state D itself with an output of 1. Similarly from A, if the input is equal to 0, it is going to state A with an output of 0, and whenever the input is equal to 1, it is going to state B with an output of 1. So from this we are going to draw this state machine, or we can say state diagram. So you can see this diagram is very simple when compared to this complex form. So this is a way that you have to simplify. So first you have to draw all the state machines, all the states you have to write, and you have to find what is the next state and the next output. So from this you have to choose those two rows which are equal. So you have to find the rows which are equal. If they are equal, we are going to eliminate one of them. Suppose if two are equal means you have to eliminate one of them. So like that we have to eliminate. And then the remaining things you have to draw, you have to write this like this simple diagram, and then you have to do this simple. So we can see this is called the simple state machine when compared to this complex state diagram. So this is a simple state diagram when compared to this complex state diagram. So now we are going to discuss about the ADC. See, ADC means, listen carefully, what is the meaning of ADC? ADC is also called as the analog to digital converter. So basically ADC is called as the analog to digital converter. So this is a block diagram which is called as the ADC. So input is basically analog in nature and output is digital in nature, or we can also call as the binary. So we can say input it is going to have only one terminal, but output can have more than one terminal, as you can see clearly in the circuit diagram itself. So one important fact that you always need to understand, which is ADC. So ADC is always going to convert the analog signal into digital signal or binary signal. So for analog signal, the input for this ADC, the input is of only one wire, but the output it can have more than one wire. So because of this, it is a digital format or binary format. So this is a simple diagram of an ADC. So this is the input and this is the output. So input is basically analog in nature and output is in the digital format or the binary format. So input is always in the analog in nature and the output is always in digital format or the binary format. So now we will discuss the types of ADC which are present in ADC, means the different types of ADCs. So now we discuss the different types of ADCs, which are the counter type ADC, SAR type ADC, flash type ADC and a dual slope ADC. So these are the different types of ADCs which are present. See, these are the things that we are going to learn one after the other in a very detailed manner. The types of ADCs are counter type ADC, and the second one is called as the flash type ADC, and the third one is called as the SAR type ADC, and the fourth one is called as the dual slope ADC. So we can say that they are basically the different types of ADCs are the counter type ADC, is also called as a RAM type ADC. Second one is the SAR type ADC. SAR means successive approximation, this one, and this is called the flash type ADC, and the last one is called as the dual slope ADC. So these are the different types of ADCs that are going to present. So counter type ADC, SAR type ADC, flash type ADC, and the dual slope ADC. So counter type ADC, SAR type ADC, flash type ADC and dual slope ADCs. So these are the different types of ADCs which are present. So now we discuss about the DAC. DAC means digital to analog converter. It is going to be the reverse operation of this ADC. So input is basically binary or the digital format, and output is in the analog nature. Means it is going to do the reverse function of the ADC. So input is basically digital format or binary format, and output is always in the analog format. So we can see clearly this is called as the DAC, and this is a simple diagram we can see clearly. So input is basically binary, means it has more than one input terminal, whereas here output is analog nature, means it is going to have only one terminal. So this you can see clearly from the circuit diagram itself. So input is basically, we can say simply digital format or binary format, and output is always in the analog format, whether it can be voltage, whether it can be current. So these are the things that you always have to keep in your mind. So therefore input is always in digital format or binary format, and the output is always in the analog, whether it can be voltage, whether it can be current. So now we will discuss the different types of DACs. So these are the two types of DACs that which are very much useful, which are called as the weighted resistor DAC and the R2R ladder type DAC. So these are the two different types of DAC we are going to study one after the other, which is called as a weighted resistor DAC, weighted resistor DAC and the R2R ladder type DAC. So these are the two types of DAC that we are going to discuss now, which is the weighted resistor DAC and the R2R ladder type DAC. Now we will discuss about the characteristics of the ADC. So now we discuss some of the important characteristics of the ADC. So we can see resolution. Resolution means it is a ratio of the voltage range by 2 to the power of n minus 1. So this is a very important point. The resolution is equal to V range by 2 to the power of n minus 1. So V range means maximum voltage minus minimum voltage. And if you want percentage resolution, it is equal to 100 by 2 to the power of n minus 1. And error should be always less than or equal to resolution. Our dynamic range is equal to 6n plus 1.8 into dB, where n is called as the number of bits. And digital output is nothing but which is basically number of steps into binary format. And number of steps is nothing but it is the ratio of the analog voltage by resolution. So these are the important points that you always have to remember. These are the important formulas that you always have to remember in the characteristics of the ADC. So ADC means I already told you, ADC means it is going to convert the analog signal into digital format. So digital format we are going to represent by n bits. So if you want to represent the digital format, we are going to represent by n bits. Then what is the resolution? It is V range by 2 to the power of n minus 1. n is called as the number of binary bits. And V range is nothing but it is equal to maximum voltage minus minimum voltage. And percentage resolution is equal to 100 by 2 to the power of n minus 1. Because if you see clearly what we are going to do is basically, see V range we are going to take it as 100%. Then what is the percentage resolution that we need to figure out? So if you see clearly, let me assume V range is equal to 100%. Then what is the resolution? I am going to assume this is 100%. So if I divide this equation 2 by equation 1, then we are going to get resolution by V range is equal to x by 100. So x is equal to resolution by V range into 100. So if you simplify this one, we are going to get which is 100 by 2 to the power of n minus 1, then x is nothing but the percentage of resolution. So therefore, we are going to assume the voltage range as 100%, then resolution is equal to x percentage. So do the ratio of second by 1, we are going to get resolution by V range is equal to x by 100. So x is equal to resolution by V range into 100. So V range cancels, we are going to get 100 by 2 to the power of n minus 1. So this we are going to call this as the percentage of resolution. So this is called as a percentage of resolution is equal to 100 by 2 to the power of n minus 1. And always error should be always less than or equal to resolution. Error should be always less than or equal to resolution. So whatever the error that you are going to get, it will be always less than or equal to resolution. And dynamic range is equal to 6n plus 1.8 into dB. So very important formula. We can say the dynamic range is equal to 6n plus 1.8 into in terms of dB, where n is called as the number of bits. So dynamic range is equal to 6n plus 1.8 into dB, where n is called as the number of bits. And digital output is nothing but digital output is nothing but it's the product of the number of steps into binary. So binary is nothing but simply digital output. The digital output is equal to number of steps into binary, and the number of steps is equal to analog voltage by resolution. So number of steps is equal to analog voltage by resolution into binary. So this is the formula that you always have to keep in your mind. Digital output is equal to analog voltage by resolution into binary. So number of steps is nothing but analog voltage by resolution. So these are the important formulas that you always have to keep in your mind. So resolution is equal to V range by 2 to the power of n minus 1, and variance is equal to maximum voltage minus minimum voltage, and percentage resolution is equal to 100 by 2 to the power of n minus 1, and error should be always less than or equal to resolution, and dynamic range is equal to 6n plus 1.8 into dB, where n is called as the number of bits, and digital output is the product of the number of steps into binary, where number of steps is nothing but it is a ratio of the, and we are going to discuss the other important concept. Listen carefully here, which is, suppose this is called as the negative feedback and op amp, negative feedback op amp, because we have given input to the negative, or we can say inverting terminal, so it is called as a inverting op amp, and the feedback is negative, so we can say inverting op amp. This is negative feedback inverting op amp. So this is the Vi, this is Ra, this is Rf, and this is V0. So if you want to figure out the what is the output voltage, so output voltage is equal to, so output voltage is equal to input voltage into minus Rf by Ra. So these derivation are already told you in the analog electronic subject. So V0 is equal to Vi into minus Rf by R1. So V0 by Vi is equal to minus Rf by R1, where Rf is called as a feedback resistor and Ra is called as an input resistance. So we are going to get this expression with the help of virtual short circuit concept, because here we can say that here it is 0 volt, as the input current here always equal to 0, so whatever this voltage should be always equal to this voltage. If it is 0 here also it is 0, so whatever the incoming current should go through here also. So if this current is I is equal to Vi minus 0 by R1, Ra is equal to 0 minus V0 by Rf. So if we equal these two equations, we are going to get V0 is equal to Vi into minus Rf by R1. So V0 by Vi is equal to minus Rf by Ra is the expression that we are going to get for this type of op amp. Suppose if you give the input here, and if you ground here, just to the vice versa, means reverse process. So basically give the input here and grounding to the here, then we can see clearly what is going to happen. So now for this op amp, if I take the ground here and if I give the input here, then as I am going to give the input to this non-inverting terminal, so places called as a non-inverting terminal and negative is called as a inverting terminal. So and it's a negative feedback, because output is given from to the negative feedback we are going to give it, because to the negative, so we are given out feedback from output to input. So this is called a negative feedback, and this is a non-inverting op amp. Then what is output voltage? Output voltage is equal to input voltage into 1 plus Rf by Ra. So output voltage is equal to input voltage into 1 plus Rf by Ra. So this is an expression that you always have to keep in your mind. So output voltage is equal to input voltage into 1 plus Rf by Ra. So this is called as the open loop op amp. So this is called as the open loop op amp. So this is called as the input voltage V1, and this is the output voltage. See, these are the two input voltages. V1 is the input voltage to the non-inverting op amp terminal, and V2 is the input voltage to the inverting terminal of the op amp. So this is the plus V reference and this is the minus V reference, and this is the output voltage V0. See, whenever V1 is greater than V2, so whenever V1 is greater than V2, we are going to get V0 is equal to plus V reference. If V2 is greater than V1, then we are going to get V0 is equal to minus V reference, or if V1 is less than V2, then we are going to get V0 is equal to minus V reference. So therefore simply we can say that whenever V1 is greater than V2, we are going to get V output is equal to plus V reference, and whenever the V2 is greater than V1 or V1 less than V2, we are going to get V0 is equal to minus V reference. Only these two voltages we can get, either plus V reference or minus V reference. Only these two voltages are possible in case of the open loop op amp, because there is no feedback. So it is called as the open loop op amp, and it's a very important point that you always have to keep in your mind. So these three important formulas that you always have to keep in your mind. Now we are going to discuss the characteristics of the DAC. See, the important characteristics of the DAC. So DAC means I have already told you, digital to analog converter. So the input is digital and the output is analog in nature. So what is the resolution? Resolution is nothing but, very simply, what the meaning of resolution is nothing but here, basically the change in analog voltage corresponding to 1 LSB bit increment at the input. So therefore you can see clearly, whenever the change in analog voltage, corresponding to 1 LSB bit increment at the input. Suppose if you are going to increase 1 LSB bit in the input, then what is the change in the analog output voltage. That is called as the resolution. So resolution means the change in analog voltage corresponding to one LSB bit increment at the input. So we can say resolution is very simple, which is whenever the resolution is very simple, the change in analog voltage corresponding to one LSB bit increment at the input is called as the resolution. The resolution formula is equal to VR by 2 to the power of n minus 1, where n is the number of bits, binary bits. So this is a very important formula that you always have to keep in your mind. So resolution is equal to VR by 2 to the power of n minus 1 means whenever there is a 1 bit increment in the LSB, then what is the change in voltage, analog voltage, that is called as a resolution. So for one LSB bit increment in the input, digital input, what is the change in the analog voltage? That is called as the resolution. So change in analog voltage corresponding to one LSB bit increment at the input. So if you are going to increment the 1 LSB bit at the input, then what is the change in analog voltage is called as the resolution. So simply we can say that here the change in analog voltage corresponding to 1 LSB bit increment at the input is called as the resolution. So resolution formula is equal to VR by 2 to the power of n minus 1. So resolution is equal to VR by 2 to the power of n minus 1. Suppose if I take VR is equal to 100%, then what is the resolution? I want to find what is the resolution in the percentage. So just do the division of these two things. Resolution by VR is equal to this. Let me assume this is x. So x by 100 is nothing but x is equal to resolution by VR into 100. So if you solve this one, we are going to get the percentage of resolution is equal to 100 by 2 to the power of n minus 1. So this is the resolution formula. The percentage of resolution is equal to 100 by 2 to the power of n minus 1. Where small n is called as the number of binary bits. So small n is called as the number of binary bits, and the VR is called as the reference input corresponding to logic 1 input, and it is also called as a full scale output voltage. So this is a very important thing that you always have to keep in your mind. So now we are going to learn about the DAC resolutions. So what is the DAC resolutions? So if you see clearly, in this they already mentioned. See, whenever there is a 1 LSB bit increment in the input, then what is the change in the output voltage, analog voltage? That is called the resolution. So resolution is equal to VR by 2 to the power of n minus 1. So change in analog voltage corresponding to 1 LSB bit increment at the input. So resolution is equal to VR by 2 to the power of n minus 1. Let me assume VR is equal to 100%. Then what is the resolution in the percentage? Let me assume this is x percentage. So do the division by 2 by equation 2 by equation 1. We are going to get resolution by VR is equal to x by 100. So x is equal to resolution by VR into 100. So in solve this one, we are going to get the percentage of resolution is equal to 100 by 2 to the power of n minus 1, where n is not called as the number of binary inputs. N is called as the number of binary inputs, and here is called as the reference input corresponding to logic 1 input. So for logic 1, what is the reference input? That is called as a VR. So reference input corresponding to logic 1 input, and is also called as a full scale output voltage. It is also called as the full scale output voltage. So now analog output voltage. So what is the meaning of analog output voltage? So I already told you this is a DAC. DAC means input is binary and output is analog. So analog output voltage is equal to resolution into decimal equivalent of binary input. Resolution into decimal equivalent of binary input. So this is a very important formula that you always need to understand. The analog output voltage is equal to resolution into decimal equivalent of binary input. So you have to do a multiplication of the resolution and the decimal equivalent of the binary input. If you do this thing, we are going to get the analog output voltage. So analog output voltage is equal to resolution into decimal equivalent of binary input. Then you are going to get the analog output voltage. So this is a very important point that you always need to keep in your mind. So analog output voltage is the product of the resolution into decimal equivalent of the binary input. So analog output voltage is the product of the resolution into decimal equivalent of the binary input. So now we discuss about the maximum analog output voltage. So what is the maximum analog output voltage that can be possible for this DAC? See, I have already told you maximum analog output voltage means VFS is called the full scale. So the full scale output voltage is equal to VFS is equal to resolution into maximum decimal value corresponding to binary bit, because I already told you very important point. The analog voltage is equal to resolution into decimal equivalent of binary input. So resolution is always constant. So whenever the decimal equivalent of binary inputs is maximum, then we are going to get the output voltage also maximum. So therefore, maximum decimal value corresponding to binary inputs is going to give you the maximum analog output voltage or full scale voltage. So therefore, full scale voltage or the maximum analog output voltage is equal to resolution into maximum decimal value corresponding to binary inputs. Then I have already told you the maximum analog output voltage or VFS is equal to resolution form just now you have seen, which is VR by 2 to the power of n minus 1 into the maximum value of decimal corresponding to binary, which is nothing but 2 to the power of n minus 1 for a bits of n. For n bits, the maximum decimal value is 2 to the power of n minus 1. So these both are going to get cancelled. So these two are going to get cancelled. Then we are going to get VR. So therefore, whatever the full scale voltage, so whatever the maximum analog output voltage is equal to VR. VR is called as the reference input corresponding to logic 1 input. So for logic 1, whatever the reference voltage itself is the maximum analog output voltage. So whatever the reference input corresponding to logic 1 input, that will be called as the maximum analog output voltage. Similarly, the full scale current is also equal to IR. IR is the current, reference input current corresponding to logic 1 input. Or VR is called as the reference input voltage corresponding to logic 1 input, and IR is called as the reference input current corresponding to logic 1 input. So this is the important point that you always have to keep in your mind. So therefore, the maximum analog output voltage or full scale voltage is equal to reference input voltage corresponding to logic 1 input, and similarly we can say the maximum analog output current is equal to, or full scale current is equal to reference input current corresponding to the logic 1 input. So these are the things that you always have to keep in your mind. So error is always less than or equal to resolution. So error will be always less than or equal to resolution, and the maximum error is equal to resolution itself. The resolution means I have already told you. The resolution means I have already told you. Whenever there is a 1 LSB bit increment, the change in analog voltage is called as the resolution. So whenever there is a 1 LSB bit increment, then what is the change in the analog voltage is called as the resolution. So this is called the resolution is nothing but 1 LSB bit increment. So whenever there is a 1 LSB bit increment at the input, the change in analog voltage is called as the resolution. So it is equal to 1 LSB bit. Then what is the minimum error? Minimum error is always equal to 0, and the maximum error is equal to resolution, and the minimum error is always equal to 0. So now, resolution, these are the two important points that you always have to keep in your mind. The resolution of the R2R ladder type DAC is equal to VR by 2 to the power of n. So for R2R ladder type DAC, the resolution is equal to VR by 2 to the power of n. There is no minus 1. So minus 1 we have to remove from the general expression. If you remove minus 1, so we are going to get this one, which is VR by 2 to the power of n. So resolution of the R2R ladder type DAC is equal to VR by 2 to the power of n. The resolution of the R2R ladder type DAC is equal to VR by 2 to the power of n. If input is BCD data, binary coded decimal data, then resolution is equal to VR by 10 to the power of n by 4 minus 1. where n is called as the number of BCD input bits. So this is a very important point that you always need to keep in your mind. These two formulas are very much important because lot of questions are being asked on these two formulas. So I request you to remember these two formulas. So therefore, the resolution of the R2R ladder type DAC is equal to VR by 2 to the power of n, and if the input is BCD data, then resolution is equal to VR by 10 to the power of n by 4 minus 1, where n is called as the number of BCD input bits. So resolution of the R2R ladder type DAC is equal to VR by 2 to the power of n, and if the input is BCD data, then resolution is equal to VR by 10 to the power of n by 4 minus 1, where n is the number of BCD input bits. So this is the point that you always need to keep in your mind. So finally I can say that in a the resolution of R2R ladder type DAC is equal to VR by 2 to the power of n, whereas if the input is BCD data, the resolution is equal to VR by 10 to the power of n by 4 minus 1, where n is called as the number of BCD input bits, where n is called as the small n is called as the number of BCD input bits. So now this is a very important table that you always need to remember this table for all your lifetime in electrical engineering, because questions have been asked on this concept. So I have drawn this table, listen carefully. Here I have already told you there are 4 types of ADCs, analog to digital converter, which is counter type, SAR type, flash type and dual slope. So these are the 4 types of ADCs: counter type, SAR type, flash type and dual slope. Now maximum clock pulses and the conversion time, and whether they are depending upon the input voltage or not, we can see clearly from here. So therefore, maximum clock pulses to get the output, the maximum clock pulses to get the output is nothing but which is 2 to the power of n minus 1 here. Then what is the conversion time? Just multiply by t clock, we are going to get 2 to the power of n minus 1 into t clock. And whether this is depending upon input voltage or not, yes, it depends upon the input voltage. It is also depends upon number of bits, and it is also depending upon number of bits in the input voltage also. Similarly, SAR type is the maximum clock pulses are n. So what is the conversion time? N into t clock. Whether it is depending upon input voltage? No, it is independent of input voltage. It only depends upon number of bits, but it is independent of the input voltage. Whereas the flash type, no matter whatever the input voltage, it takes only 1 clock pulse to get the output. So what is the conversion type? Multiply by t clock, we are going to get t clock. Whether it is depending on input voltage now, it is not at all dependent upon input voltage. It is not dependent upon the number of bits also. So now dual slope. Dual slope is nothing but it is going to the maximum clock pulses required to detect this analog input. See, basically this ADC is nothing but analog input and digital output. So whatever this analog input, we have to detect with the help of binary output. So we have to get a corresponding binary output for this analog input. How much time it is going to take? It is going to take 2 to the power of n plus 1 clock pulses, means 2 to the power of n plus 1 into t clock, and is also depending upon the input voltage. As the input voltage changes, this clock time is also going to get changes. So therefore we can say it is depending upon number of bits, and also it is depending upon the input voltage. So these are the things that you need to understand from this here. So this is the easy way to remember. The easy way to remember this is, see, Captain Sachin first duckout. Very easy to remember. Captain Sachin first duckout. So like this you have to remember. So Captain Sachin first duckout. So C means counter type. So C means counter type. S means SAR and F means flash type, and D means dual slope. So Captain Sachin first duck out. So Captain Sachin first duck out means counter type ADC, SAR type ADC, flash type ADC and dual slope ADC. So this is to the power of n minus 1 and this is n, this is 1, this is to the power of n plus 1. So just multiply by t clock here, we are going to get these expressions. This, do remember this one, into correct, cross, you can say correct. So like this, that you can easily remember this table. So in the examinations it will be very easier for you to answer the questions. So easy to remember is the different types of ADCs are Captain Sachin first duck out means counter type, SAR type, flash type and dual slope. This is in the maximum clock pulses. The maximum clock pulses to detect the analog input which is to the power of n minus 1. This is n, this is 1 and this is to the power of n plus 1. So just multiply by t clock, we are going to get to the power of n minus 1 into t clock, n into t clock, to the power of n plus 1 into t clock. Here, yes, no, yes. So like this you can say clearly. So finally I can say that this counter type is depending upon the number of bits and also on the input voltage. Whereas the SAR type, it is depending upon number of binary bits and but it is independent of the input voltage. Whereas the flash type, it is independent of number of bits and it is also independent of input voltage. Analog input voltage means analog voltage. And also dual slope, it is depending upon number of binary bits and also it is depending upon the input analog voltage. So these are tables that you always need to keep in your mind. So the types of ADCs are the Captain Sachin first duck out means counter type, SAR type, flash type and dual slope. This is to the power of n minus 1. So this is n, this is 1 to the power of n plus 1. So just multiply by t clock. So to the power of n minus 1 into t clock, n into t clock, this is t clock and this is to the power of n plus 1 into t clock. So this is basically number of maximum clock pulses to detect the analog voltage to the corresponding binary output. So here it's a conversion done. This much amount of time is taken and this is depending on the input voltage. It is not dependent upon input voltage. It is not dependent upon input voltage and it depends upon the input voltage. So this table that you always need to keep in your mind.